Hello there, and welcome to Cosmos for Sleep. Tonight, we're embarking on a gentle journey through our own cosmic neighborhood, the solar system. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. The Sun accounts for 99.8% of the entire solar system's mass, dominating its gravitational pull. This central star, a radiant heart, holds everything within its vast gravitational embrace. Its immense presence shapes the orbits and movements of every planet, moon, and smaller body, orchestrating a silent, grand cosmic ballet. Without this singular, powerful influence, our familiar system would simply not exist in its current, harmonious form. This profound dominance of the Sun's mass is the very foundation upon which our solar system is built. It is this overwhelming gravitational field, an invisible yet undeniably potent force that acts as the unbreakable tether, binding all the planets, dwarf planets, asteroids, and comets into their graceful, predictable orbits. From the swift, rocky worlds closest to its warmth, to the distant, icy realms far beyond Neptune, every single object within our cosmic home is intricately linked to the Sun's commanding pull. This deep gravitational connection is not a sudden, dramatic force, but a constant, pervasive presence, ensuring the harmonious order and enduring stability of our planetary neighborhood. The Sun's sheer bulk, representing nearly all the matter in the solar system, allows it to maintain this overarching control, a silent, powerful guardian presiding over our cosmic family. This immense concentration of mass at the center ensures that all other bodies revolve in a delicate equilibrium, a testament to the Sun's ultimate authority in this vast, tranquil expanse. The planets, in their patient journeys, are forever influenced by this colossal anchor, their paths woven into the fabric of the Sun's pervasive gravity, creating the serene, predictable rhythms we observe across billions of miles. It is a subtle, yet absolute form of cosmic governance, a gentle hand guiding the celestial dance. To truly appreciate the Sun's majestic grandeur, one must consider its staggering physical dimensions. 1 million Earths could comfortably fit inside the Sun, showcasing its immense size. Let us take a moment to gently imagine this colossal scale. Envision our familiar homeworld, with its swirling blue oceans, its verdant green continents, its towering mountain ranges, and its expansive, ever-changing skies. Now, try to picture a million such vibrant worlds, each unique and teeming with its own delicate ecosystems and intricate geographies, all nestled with ease within the embracing, gargantuan sphere of our star. This quiet thought experiment helps us to grasp the truly astounding physical dimensions of our Sun, a furnace of light and warmth that stretches beyond our everyday comprehension. Its vast, perfectly spherical form commands the absolute center of our solar system, a magnificent testament to the powerful, shaping forces of gravity that meticulously crafted it from a primordial cloud of gas and dust. This singular, expansive orb, so much grander and more voluminous than any planet orbiting it, provides an unwavering anchor, both visually and gravitationally, for all the celestial bodies that dance around it in their measured ancient paths. The very light that bathes our planet, sustaining all forms of life, originates from this immense radiant source, a constant, tranquil emanation streaming across the silent void, a timeless reminder of its majestic, enduring presence in the cosmic tapestry. Its sheer volume ensures that it remains the undisputed giant, effortlessly holding its court of planets in a perpetual, graceful waltz. Deep within this colossal, luminous star lies its fiery, energetic heart, a region of profound intensity where the Sun's core reaches astonishing temperatures of 15 million degrees Celsius. It is in this incredibly hot and dense central region that the sublime and powerful process of nuclear fusion takes place. Here, under conditions of unimaginable pressure and extreme thermal energy, hydrogen atoms are gently coaxed to combine or fuse, forming new atoms of helium. This delicate cosmic alchemy, occurring ceaselessly, releases an immense and continuous stream of energy, a steady inner glow that powers our entire star. The conditions required for this intricate process are truly extraordinary, far exceeding anything we can replicate or even fully experience on Earth. Yet it is this stable, internal furnace that provides the boundless energy radiating outward, sustaining our entire solar system. This constant internal warmth is the very essence of the Sun's being. A perfectly stable engine humming softly and reliably at the heart of our cosmic home, ensuring its consistent output. The Sun's core is a realm of such profound activity that it shapes everything about the star, from its outward appearance to its life-giving warmth. It is a testament to the elegant yet powerful processes at play in the heart of a star, generating the very light and heat that allow our world to thrive. As a direct and awe-inspiring consequence of this ceaseless internal process, the Sun converts about 4 million tons of matter into energy every second through nuclear fusion. This staggering, almost incomprehensible rate of conversion is what perpetually fuels the Sun's brilliant luminosity and its constant, life-giving warmth. Each passing second, an almost imperceptible amount of its colossal mass transforms into pure, radiant energy, a gentle cascade of photons that streams outward across the boundless vacuum of space. This energy manifests as sunlight, a pervasive and comforting glow that travels patiently, bathing our planets in its vital warmth and illuminating their surfaces. This continuous process has been unfolding with unwavering consistency for billions of years, a testament to the Sun's enduring power and its central role as the primary energy source for all life on Earth. It is a profound demonstration of the universe's elegant and fundamental laws, where matter and energy are intertwined in a ceaseless, wondrous exchange, a constant cosmic alchemy that ensures the continuation of warmth and light throughout our planetary system. The gentle outflow of this converted energy is what allows plants to grow, oceans to warm, and life to flourish, a subtle yet mighty testament to the Sun's quiet generosity. Our Sun is scientifically classified as a G-type main sequence star, often referred to by astronomers as a yellow dwarf, though in truth, its actual light is perceived as white. The designation yellow dwarf can be a little misleading to the casual observer, as its inherent color, when viewed from the pristine vantage point of space, is a pure, brilliant white. It only appears with a yellowish tint to our eyes here on Earth due to the subtle filtering effects of our planet's atmosphere, which scatters blue light more effectively. Being a main sequence star signifies that our Sun is currently in the most stable and longest phase of its stellar existence. During this tranquil period, it steadily fuses hydrogen into helium within its deep core, maintaining a balanced and consistent energy output. This classification places it among a vast and numerous population of stars throughout the cosmos that are also in a similar, peaceful stage of their stellar evolution. This remarkable stability is a key factor in the long-term habitability of Earth, providing a reliable and consistent energy output that has nurtured life for billions of years. Its gentle, unwavering radiance is a steadfast beacon, patiently guiding and warming our entire solar system with an enduring and dependable consistency, a silent promise of continued illumination. The radiant energy that emanates from this brilliant white star embarks on an incredible and unhurried journey across the silent void of space. It takes light from the Sun approximately 8 minutes and 20 seconds to reach Earth. Despite light being the fastest entity known in the universe, traveling at an astonishing speed of approximately 299,792 kilometers per second, or 186,282 miles per second, the immense distance between the Sun and Earth means that this measured delay is always present. This fascinating cosmic lag means that when we gaze upon the sun or feel its gentle warmth on our skin, we are not experiencing it exactly as it is in that very moment, but rather as it appeared a little over 8 minutes in the past. It is a subtle yet profound reminder of the vastness of space and the unhurried pace of cosmic communication. This constant, unceasing flow of light, traveling patiently and purposefully across millions of miles, is what illuminates our days, defines our seasons, and powers the delicate, intricate ecosystems of our world. Each photon, having begun its journey moments ago, brings with it the ancient story of the sun's enduring light. Our steadfast and enduring sun is estimated to be about 4.6 billion years old, marking it as a mature and venerable celestial body within the grand cosmic timescale. This significant age places it roughly halfway through its stable main sequence phase, the longest and most tranquil period of its life, where it consistently fuses hydrogen into helium in its core. This exceptionally long and patient lifetime provides a profound sense of cosmic continuity and reliability. For billions of years, the sun has graced our solar system with its unwavering warmth and consistent light, serving as a constant, dependable presence in the unfolding cosmic drama. Scientists estimate it has another 5 billion years of stable burning ahead before it begins its gentle, gradual transformation. In the distant, far-off future, it will slowly expand into a red giant, gracefully shedding its outer layers to form a beautiful, ethereal planetary nebula, before eventually settling into a serene and compact white dwarf star. This long, predictable life cycle is a reassuring thought, a testament to the stable, enduring nature of our home star and the gentle, unhurried progression of cosmic time, a silent promise of billions more years of steady radiance before its final, graceful, cosmic change. As our sun continues its patient, luminous journey, we turn our gaze inward towards the two closest planetary companions, Mercury and Venus, each a world of remarkable and often surprising characteristics. Among these inner rocky worlds, Venus presents a particularly fascinating rhythm. A day on Venus is longer than its year, taking 243 Earth days to rotate on its axis, but only 225 Earth days to complete a full orbit around the Sun. Imagine a world where the slow, deliberate turning of the planet means that the sunrise, once begun, would stretch across what feels like an eternity to our earthly senses, only to be followed by an equally prolonged and unhurried sunset. This exceptionally leisurely rotation creates a unique temporal experience, where the cycles of light and darkness unfold with an almost imperceptible slowness compared to our own planet's brisk 24-hour spin. The Sun, as viewed from the Venusian surface, would appear to crawl across the sky, taking many Earth months to traverse from one horizon to the other. This gentle, drawn-out celestial dance is a testament to the subtle gravitational and rotational forces that have shaped this planet over billions of years, creating a day that defies our intuitive understanding of planetary motion. The very concept of a Venusian day becomes a sprawling, patient epoch, a long, quiet passage of time that slowly unwinds as the planet makes its way around its solar parent. This extended period of rotation means that different regions of Venus are exposed to the Sun's direct radiance for prolonged durations, leading to particular atmospheric patterns that are unique to this world, further contributing to its distinctive character within our solar system. Adding to Venus's distinctiveness is its unusual rotational direction. Venus rotates clockwise, a retrograde motion, unlike most other planets in our solar system. While the majority of planets in our cosmic neighborhood spin in a counterclockwise direction, when viewed from above the Sun's north pole, Venus gracefully turns in the opposite manner. This peculiar backward spin sets it apart, a cosmic anomaly that has long intrigued astronomers. Scientists believe this unusual rotation might be the result of a colossal impact with another celestial body in its distant past, an ancient, gentle collision that subtly altered its rotational momentum. Alternatively, it could be a consequence of complex gravitational interactions with the Sun and other planets over vast timescales, slowly guiding it into this unique orientation. Regardless of its origin, this retrograde rotation contributes to the extended length of its day, as the planet's spin works against the direction of its orbital motion. The serene, unhurried turning of Venus in this reverse direction paints a picture of a world following its own quiet, independent path, a testament to the diverse and sometimes unexpected outcomes of cosmic evolution. This singular characteristic adds another layer of quiet mystery to our understanding of this cloud-shrouded neighbor, a planet that truly dances to its own measured, unhurried rhythm. The atmosphere of Venus is composed almost entirely of carbon dioxide, creating a runaway greenhouse effect that dramatically shapes its surface conditions. This incredibly dense and pervasive atmospheric blanket, far thicker than Earth's, acts like an insulating shield, effectively trapping the sun's warmth and preventing it from radiating back into space. The carbon dioxide molecules, abundant and tightly packed, absorb thermal energy with remarkable efficiency, leading to a relentless and extreme warming of the planet's surface. This constant, gentle accumulation of heat has transformed Venus into a world of intense, pervasive warmth, where the ground itself glows with a subtle, infernal heat. The delicate balance of energy that we experience on Earth, where some solar radiation is absorbed and some is reflected, is entirely absent on Venus. Instead, the heat is held captive, creating an environment that is consistently and profoundly warm across its entire landscape, untouched by the cooling breezes that might otherwise offer a momentary respite. This pervasive, heat-trapping effect is a powerful demonstration of how atmospheric composition can fundamentally alter a planet's climate, creating a world of quiet, enduring thermal intensity. Consequently, despite being farther from the Sun than Mercury, Venus is hotter than Mercury due to its thick, heat-trapping atmosphere. This might seem counterintuitive at first glance, as one would naturally expect the planet closest to the Sun to experience the most intense heat. However, Venus's dense carbon dioxide atmosphere completely alters this expectation. While Mercury, being the innermost planet, receives a greater direct intensity of solar radiation, it lacks a substantial atmosphere to retain that heat. Venus, on the other hand, with its potent greenhouse effect, effectively captures and holds on to the warmth it receives, accumulating it over time. The constant, tranquil embrace of its thick atmospheric blanket ensures that the surface temperature remains uniformly high, day and night, across the entire planet. This creates a pervasive, unyielding warmth that far surpasses even the scorching daytime temperatures of Mercury. It is a striking example of how a planet's atmospheric composition can be a more significant factor in determining its surface temperature than its mere proximity to its star, revealing a subtle complexity in the thermal dynamics of our solar system's inner worlds. The silent, efficient work of Venus's atmosphere transforms it into a gentle furnace, radiating a warmth that never truly dissipates. In stark contrast to the pervasive warmth of Venus, Mercury experiences the most extreme surface temperature variations in the solar system, from over 427 degrees Celsius during its prolonged day to a chilling minus 179 degrees Celsius at night. This astonishing temperature swing, spanning more than 600 degrees Celsius, creates a landscape of unparalleled thermal extremes. During the lengthy periods when one side of Mercury faces the Sun, it is bathed in an intense, unyielding solar radiance, causing its rocky surface to heat to incandescent levels, hot enough to melt lead. Yet, as the planet slowly rotates and that same surface turns away from the Sun, plunging into its equally prolonged night, the absence of atmospheric insulation allows the accumulated heat to rapidly dissipate into the cold vacuum of space. The transition from scorching day to frigid night is a dramatic testament to the planet's unique thermal environment, where the very rocks of its surface endure a constant, profound shift between intense heat and deep cold. This cosmic rhythm of extreme temperature changes creates a landscape that is both harsh and profoundly quiet, a world of silent, unceasing thermal flux, endlessly cycling between fiery warmth and icy stillness. The primary reason for Mercury's dramatic thermal shifts is that it has no atmosphere to trap heat, leading to its dramatic temperature swings. Unlike Earth's protective and insulating blanket of air, or Venus's thick, heat-retaining shroud of carbon dioxide, Mercury exists in an almost perfect vacuum. Any solar energy that reaches its surface is either absorbed or reflected, but very little is retained or redistributed. Without an atmospheric layer to circulate warmth from the sunlit side to the shadowed side, or to hold onto heat during the long nights, the planet's surface temperatures fluctuate wildly. The solar winds, unhindered by atmospheric resistance, directly interact with its exposed surface, creating a stark, unimpeded exchange of energy with the cosmos. This absence of an atmospheric buffer means that Mercury's surface is fully exposed to the harsh realities of space, experiencing the sun's direct, unfiltered radiance and the deep, pervasive cold of the vacuum with equal intensity. It is a world stripped bare, its naked surface patiently absorbing and releasing warmth in a continuous, unmediated cycle. This fundamental characteristic defines Mercury's thermal environment, making it a world of silent, extreme contrasts, a testament to the crucial role an atmosphere plays in moderating a planet's climate. A final shared characteristic between these two innermost worlds, Mercury and Venus, is that both lack natural moons, a distinction shared only by these two inner planets within our solar system. Unlike Earth, which is graced by its single luminous lunar companion, or the outer planets with their extensive retinues of diverse satellites, Mercury and Venus journey around the Sun in solitary splendor. This absence of natural moons contributes to their quiet isolation within the inner solar system, highlighting a subtle difference in their gravitational histories compared to our own planet. Scientists believe that this lack of moons might be due to their close proximity to the Sun, where the Sun's immense gravitational pull could have either prevented the formation of moons or stripped away any that might have formed in the distant past. It is also possible that any early moons may have simply merged with their parent planets over billions of years, a gentle, unhurried process of cosmic integration. This shared characteristic of being moonless worlds adds to their unique identities, painting a picture of two planets that navigate their orbital paths without the delicate gravitational dance of a celestial partner. They float serenely, quietly, and alone, a testament to the varied outcomes of planetary formation within our tranquil solar system. As these two innermost worlds complete their solitary orbits, our journey now turns to our own familiar blue sphere, Earth, and its steadfast companion, the Moon. Our home planet holds a unique distinction among its celestial neighbors. Earth is the only planet in our solar system not named after a Roman or Greek deity. While Mercury takes its name from the swift messenger god, and Venus from the goddess of love and beauty, Earth carries a name rooted in ancient Germanic languages, meaning simply ground or soil. This humble origin speaks to a profound connection to the very substance that forms our world, a grounding identity that sets it apart from the grand mythological pantheon. It is a name that quietly echoes its role as a foundation, a place of stable ground and nurturing soil, a haven for life in the vast expanse of space. This simple, earthy designation reflects the planet's essence, a place of tangible substance and sustained existence, a contrast to the ethereal, godlike names bestowed upon the other wandering stars in our sky. It reminds us of the quiet strength and enduring presence of our planetary home, a world defined by its tangible reality rather than by ancient tales. Our celestial companion, the Moon, maintains a subtle yet ceaseless dance with our planet, a relationship that is slowly, almost imperceptibly, evolving. The Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. This gradual recession, while seemingly small, adds up to significant distances over the immense stretches of cosmic time. It is a patient, unhurried process, driven by the intricate gravitational interactions between Earth and its moon. As the moon's gravity gently pulls on Earth's oceans, it creates tidal bulges. Earth, rotating beneath these bulges, experiences a gentle friction that transfers a tiny amount of rotational energy to the moon. In turn, this minuscule addition of energy causes the moon to spiral ever so slightly outward, gradually increasing its distance from us. This slow, elegant drift is a testament to the dynamic, ever-changing nature of celestial mechanics, where even the most stable relationships are subject to subtle, long-term shifts. Over millions and billions of years, this imperceptible outward movement has shaped the moon's orbit and influenced Earth's rotation, a quiet, continuous reshaping of our shared cosmic environment. It is a testament to the enduring, yet ever-evolving bond between our planet and its luminous satellite, a slow, patient unfolding of cosmic destiny. Deep within Earth's heart, a silent, powerful engine tirelessly works to protect all life on its surface. Earth's molten outer core generates a powerful magnetic field that protects us from solar radiation. This invisible shield, often referred to as the magnetosphere, is born from the gentle churning and convection of liquid iron within our planet's outer core, creating vast electric currents that extend far into space. Like a protective, ethereal cocoon, this magnetic field gracefully deflects harmful charged particles, primarily from the sun's constant outflow of solar wind and more energetic cosmic rays. Without this powerful, pervasive barrier, these high-energy particles would relentlessly bombard Earth's surface, stripping away our atmosphere and making life as we know it impossible. It is a quiet, yet utterly vital guardian, a constant, unseen embrace that safeguards our delicate biosphere. This intricate internal process ensures a stable and serene environment, allowing the gentle rhythms of life to flourish undisturbed by the harsh conditions of interstellar space. The magnetic field is a profound testament to Earth's self-sustaining mechanisms, a silent, enduring protector woven into the very fabric of our planet's being, ensuring a tranquil and safe harbor for all. This intimate gravitational connection with the moon also subtly influences our planet's own internal rhythm. The Earth's rotation is gradually slowing down, making days slightly longer over vast geological timescales. This unhurried deceleration is primarily a consequence of the moon's gravitational pull on Earth's oceans, creating the tides. The friction generated by the movement of these tidal bulges across the ocean floor acts as a gentle brake on Earth's rotation. While the effect is incredibly subtle, amounting to only a few milliseconds per century, it is a persistent force that has profoundly shaped Earth's rotational period over billions of years. In the distant past, Earth's days were significantly shorter, perhaps as little as 6 hours long. This gradual, patient lengthening of our days is an ongoing, imperceptible process, a testament to the enduring gravitational dialogue between Earth and its lunar companion. It is a slow, rhythmic adjustment, a quiet rebalancing of angular momentum that unfolds with an almost majestic slowness, weaving the cosmic dance into the very fabric of our planet's temporal cycles. This steady, unhurried change is a quiet reminder of the deep, interconnected nature of our solar system. Our moon, often perceived as a simple orb in the night sky, holds a remarkably prominent place among the solar system's satellites. Our moon is the fifth largest moon in the solar system and is unusually large compared to its parent planet. While many planets host numerous moons, few possess a satellite of such significant relative size. To put its scale into perspective, the moon's diameter is more than 1/4 that of Earth, a proportion rarely seen in other planetary systems. This unusual grandeur is believed by scientists to be the result of a colossal impact event in the early solar system, where a Mars-sized body gently collided with a nascent Earth, gradually coalescing to form our majestic companion. This theory suggests a singular, profound birth for our moon, one that endowed it with its remarkable size and stable orbit. Its substantial presence exerts a powerful gravitational influence on Earth, acting as a stabilizing force on our planet's axial tilt, which in turn contributes to the relatively stable climate patterns that have allowed life to flourish. This unusually large and significant lunar presence is not merely a distant light, but an integral part of Earth's cosmic identity, a quiet, enduring partner in our planetary journey. The most tangible and immediate evidence of this enduring partnership is found in the rhythmic pulse of our planet's oceans. The moon's gravitational pull creates ocean tides on Earth, a subtle dance between celestial bodies. As the moon orbits our planet, its gravitational force gently tugs at Earth's water, creating bulges on both the side of Earth facing the moon and on the opposite side. Our planet then rotates through these bulges, leading to the familiar ebb and flow of high and low tides that grace our coastlines twice each day. This ceaseless, rhythmic motion of the waters is a direct, observable consequence of the moon's pervasive gravitational presence, a silent and ancient dialogue between two celestial bodies. It is a testament to the moon's enduring influence, shaping the very edges of our continents and stirring the vast depths of our seas. This constant, unhurried cycle of rising and falling waters highlights the delicate balance of forces at play, a harmonious interaction that has sculpted coastlines and influenced marine life for billions of years, a tranquil, predictable rhythm in the grand cosmic symphony. Finally, enveloping our world in a protective, life-sustaining embrace is the very air we breathe. Earth's atmosphere is a delicate blend of nitrogen, oxygen, argon, and other gases vital for life. This translucent, ethereal blanket, extending hundreds of miles above the surface, is a finely tuned composition that has allowed complex life to emerge and thrive. Nitrogen, making up about 78%, acts as a gentle diluent, moderating the reactivity of oxygen. Oxygen, at around 21%, is the essential gas that fuels respiration for countless organisms. Argon and a trace of other noble gases, along with water vapor and carbon dioxide, complete this intricate mixture. Beyond providing the necessary gases for breathing, the atmosphere also acts as a thermal regulator, gently trapping some of the sun's warmth to maintain a habitable temperature range, preventing the extreme fluctuations seen on moonless, airless worlds. It also serves as a protective shield, gently incinerating incoming meteoroids before they can reach the surface. This serene and complex atmospheric veil is a testament to Earth's unique planetary conditions, a delicate, vital embrace that cradles and sustains all forms of life, a quiet, breathing presence that defines our habitable home in the vastness of space. From the life-sustaining embrace of Earth's atmosphere, our celestial journey now extends outward to our intriguing neighbor, Mars, often known as the Red Planet. Mars holds a truly awe-inspiring geological marvel. Olympus Mons on Mars is the highest mountain and largest volcano in the solar system, standing 3 times taller than Mount Everest. Imagine a vast, shield-shaped mountain, so immense that its gentle slopes would barely be perceptible from its base, stretching across a region larger than the state of Arizona. This colossal dormant volcano rises majestically from the Martian plains, its summit piercing the thin atmosphere to an elevation of over 21 kilometers or 13 miles. Its sheer scale is a quiet testament to a past era of profound geological activity on Mars. When immense plumes of molten rock slowly erupted and accumulated over billions of years, building this monumental structure, the low gravity on Mars, combined with the absence of shifting tectonic plates, like those on Earth, allowed volcanic flows to continuously build upon themselves, culminating in this singular, breathtaking peak. Olympus Mons stands as a silent sentinel, a majestic, ancient monument to the powerful, shaping forces that have gently sculpted the Martian landscape over cosmic time, a testament to the planet's grand and unhurried geological history. Its presence suggests a world that once experienced a very different, yet equally serene, internal dynamism, slowly crafting this unparalleled landmark that remains one of the most iconic features in our solar system. The sheer volume of material that formed this mountain speaks to an enduring, patient process of planetary formation and evolution, where gravity and internal heat worked in quiet concert to create such an immense and captivating structure. Beyond its towering peaks, geological evidence reveals a vastly different past for the red planet. Scientists believe that Mars once had liquid water flowing on its surface and a much thicker atmosphere, as evidenced by geological features. Gentle, winding river valleys, ancient lake beds, and mineral deposits that typically form in the presence of water are quietly etched across the Martian landscape, telling a story of a warmer, wetter world billions of years ago. These subtle geological imprints suggest a time when Mars might have harbored a more Earth-like environment, where water flowed freely, perhaps even supporting a primitive form of life. The presence of a thicker atmosphere would have been crucial, providing the necessary pressure and insulation to keep liquid water stable on the surface, preventing it from boiling away into space or freezing solid. Over vast stretches of cosmic time, however, Mars gradually lost much of its atmosphere to the relentless solar wind, a gentle stripping away of its protective veil. This loss led to a gradual cooling and drying of the planet, transforming it into the cold, arid world we observe today. The ancient riverbeds and dried-up lake beds stand as silent reminders of this profound planetary transformation, whispering tales of a long-lost watery past, a testament to the slow, unhurried evolution of a planet that once held the promise of liquid oceans. This quiet, geological record allows us to peek into a bygone era, understanding how even familiar planets can undergo dramatic yet serene shifts in their environmental conditions, highlighting the subtle dance of atmospheric escape and solar influence. Further out in its orbital embrace, Mars is accompanied by two small, irregularly shaped moons, Phobos and Deimos, which are thought to be captured asteroids. These two diminutive celestial bodies are not spherical like Earth's moon, but rather resemble potatoes, with uneven surfaces and numerous craters. Their irregular forms and close orbits suggest that they did not form alongside Mars from the same primordial disk of material, but were instead gravitationally snared by the red planet's pull sometime in the distant past. As they drifted too close to Mars, perhaps on a leisurely journey through the asteroid belt, the planet's gravity gently guided them into stable, albeit eccentric orbits. Phobos, the larger and closer of the two, is slowly spiraling inward and is predicted to either gently break apart or merge with Mars in about 50 million years, a slow, unhurried end to its cosmic dance. Deimos, the smaller and more distant moon, maintains a more stable, yet equally patient, orbit. These two quiet, captured companions offer astronomers valuable insights into the gravitational dynamics of planetary systems and the processes by which celestial bodies can be subtly drawn into new cosmic relationships, adding to the quiet complexity of our solar system's architecture. Their presence is a testament to the enduring, subtle gravitational forces that constantly reshape and reconfigure the smaller elements within our cosmic neighborhood. The most striking visual characteristic of this planet and the source of its popular moniker is its distinct red color. The distinct red color of Mars comes from iron oxide, or rust, in its soil. This pervasive reddish hue, visible even from Earth, is not merely a superficial coating, but an integral part of the Martian regolith, the loose surface material that covers the planet. Billions of years of exposure to oxygen, likely released from past water or atmospheric processes, cause the iron-rich rocks and dust to slowly oxidize, creating vast expanses of rust-colored terrain. This subtle chemical transformation, unfolding with an unhurried grace over eons, has painted the entire planet in shades of ochre, crimson, and burnt orange, giving it its iconic appearance. The dust, suspended in its thin atmosphere, further scatters this reddish light, lending the Martian sky a soft, salmon-pink glow. This quiet, chemical process has profoundly shaped the visual identity of Mars, making it a uniquely captivating world in our night sky, a testament to the slow, patient interactions between planetary geology and atmospheric chemistry. creating a landscape that is both beautiful and profoundly serene in its coloration. Despite its stark differences from Earth, Mars exhibits a familiar rhythm in its celestial mechanics. Seasonal changes on Mars are similar to Earth's, with polar ice caps that grow and shrink. Just like our home planet, Mars is tilted on its axis, leading to different regions receiving varying amounts of sunlight throughout its orbit around the Sun. This axial tilt, similar in angle to Earth's, results in distinct Martian seasons, each unfolding with a quiet predictability. During the Martian winter, the polar ice caps, composed of both water ice and frozen carbon dioxide, expand significantly, gently accumulating layers of frost. As spring arrives and summer progresses in each hemisphere, these brilliant white caps slowly recede, releasing carbon dioxide back into the atmosphere and subtly altering atmospheric pressure. This seasonal dance of expansion and contraction is a mesmerizing display of planetary meteorology, a slow, patient exchange of volatiles between the surface and the atmosphere. It highlights a common thread in the orbital mechanics of our solar system, where axial tilt plays a crucial role in shaping the environmental cycles of planets, creating a beautiful, unhurried ballet of ice and atmosphere that unfolds across the Martian landscape, a distant echo of Earth's own seasonal rhythms. Looking towards the future, Mars continues to hold a profound allure for humanity. Future human missions to Mars are being planned, aiming to establish a presence on another planet. Scientists and space agencies across the globe are diligently working on developing the technologies, strategies, and infrastructure necessary to transport astronauts to the Red Planet, sustain them there, and eventually return them safely to Earth. These ambitious plans envision a gentle expansion of human presence beyond our home world, a patient and measured step towards becoming a multiplanetary species. Establishing a sustained human presence on Mars could involve building habitats, developing methods for resource utilization, and conducting long-term scientific research that deepens our understanding of planetary evolution and the potential for life beyond Earth. This quiet, purposeful endeavor is driven by a deep human curiosity and an enduring desire to explore, to reach out and touch another world. The meticulous planning and gradual technological advancements represent a slow, deliberate unfolding of humanity's cosmic aspirations, a testament to our gentle yet persistent drive to expand our horizons and establish new footholds in the vast, serene expanse of our solar system, preparing for a future where humanity might softly tread upon the red dust of another world. As we gently drift past Mars, our cosmic journey leads us to a fascinating and often misunderstood region of our solar system, the asteroid belt. The asteroid belt, located between the orbits of Mars and Jupiter, is vast, but individual asteroids are typically millions of miles apart, not densely packed. When depicted in films or popular media, this cosmic neighborhood is often shown as a chaotic, densely crowded field of tumbling rocks, making perilous passage for any spacecraft. In reality, the asteroid belt is an immense, sprawling expanse of space, so expansive that the average distance between any two sizable asteroids is millions of kilometers. This means that navigating through the belt is far from a dangerous obstacle course. A spacecraft can traverse it with relative ease, encountering very few objects along its path. The sheer volume of space within the belt, combined with the relatively small size of most asteroids, ensures that these remnants of the early solar system maintain a respectful and peaceful distance from one another. This tranquil, unhurried separation allows each asteroid to follow its own gentle orbital path without frequent, dramatic encounters. It is a testament to the quiet order that prevails even in regions of concentrated cosmic debris, where the vastness of space ensures a serene, uncrowded journey for any silent explorer. The impression of a chaotic jumble is replaced by a vision of a subtle, dispersed collection of ancient cosmic building blocks, each patiently tracing its own long elliptical route around our central star. Within this expansive, thinly populated belt resides its most significant inhabitant, Ceres. The largest object in the asteroid belt is also classified as a dwarf planet. Unlike the irregularly shaped asteroids that surround it, Ceres is massive enough for its own gravity to have gently pulled it into a nearly spherical form, a defining characteristic of a dwarf planet. This celestial body, with a diameter of about 940 kilometers, or 585 miles, holds a unique position, bridging the gap between the smaller, more numerous asteroids and the larger, more prominent planets. Scientists believe that Ceres possesses a differentiated interior, meaning it has distinct layers, possibly including a rocky core and a mantle of water ice, perhaps even with a subsurface ocean. The presence of water ice is particularly intriguing, as it offers clues about the distribution of volatiles in the early solar system and the potential for chemical processes. Ceres orbits the Sun quietly and steadily, a tranquil, luminous presence within the asteroid belt, a testament to the diverse forms that celestial bodies can take in our cosmic neighborhood. Its classification as a dwarf planet highlights its substantial nature and its importance as a unique world in its own right, a serene and ancient body that patiently reveals the subtle complexities of planetary evolution. These numerous smaller bodies that populate the belt are, in essence, cosmic fossils. Asteroids are rocky, airless remnants from the early formation of our solar system. These diverse objects, ranging in size from tiny pebbles to hundreds of kilometers across, represent the primordial building blocks that never quite coalesced into a full-fledged planet. Approximately 4.6 billion years ago, as our solar system was slowly taking shape from a swirling cloud of gas and dust, these rocky fragments were left behind, unable to fully combine due to the immense gravitational influence of the nearby giant planet Jupiter. Instead of forming a single large planet, they remained scattered, patiently orbiting the Sun in their designated region. Each asteroid carries within its stony composition the chemical signatures of that ancient era, offering scientists invaluable insights into the conditions and materials present during the birth of our planetary system. They are silent witnesses to the turbulent yet creative processes of cosmic formation, small, enduring pieces of a grander, unfolding story. These airless wanderers, each a unique fragment of cosmic history, continue their unhurried journey, preserving the subtle echoes of creation in their weathered surfaces, a tranquil reminder of the solar system's formative years. Despite the vast numbers of individual asteroids, their collective mass is surprisingly modest. The total mass of the asteroid belt is less than the mass of Earth's moon. This fact often comes as a quiet revelation, especially given the common perception of a crowded, substantial belt. If one were to gather all the asteroids, large and small, and combine them into a single celestial body, its mass would still be less than that of our familiar lunar companion. This relatively low total mass indicates that the asteroid belt is primarily composed of smaller fragments, and that a significant amount of material that might have formed a planet was either ejected from the solar system or incorporated into other bodies during the early, more chaotic stages of formation. The gravitational dominance of Jupiter played a crucial role in preventing these scattered remnants from fully coalescing, gently stirring the region and preventing the formation of a larger, unified planet. This subtle, yet profound gravitational influence ensured that the material remained dispersed, a collection of smaller, individual pieces, rather than a singular, massive world. The asteroid belt, therefore, is a quiet, sparsely populated region, a testament to the elegant gravitational forces that shape the distribution of matter in our solar system, revealing a delicate balance of cosmic influences. The visual appearance of most asteroids further distinguishes them from the larger, more familiar planets. Many asteroids are not spherical, but have irregular shapes due to their relatively small size and weak gravity. Unlike planets and dwarf planets, which possess sufficient mass for their own gravity to pull them into a rounded, hydrostatic equilibrium, the majority of asteroids are simply too small to achieve this spherical form. Their gravitational fields are relatively weak, unable to overcome the internal strength of their rocky structures. As a result, they retain the irregular, jagged, or elongated shapes they acquired during their formation or from subsequent, gentle collisions. These diverse and often peculiar forms are a quiet testament to their unique histories, each lump and crater telling a silent story of ancient impacts and unhurried cosmic weathering. From elongated peanut-like shapes formed by two smaller asteroids gently merging, to fragmented, angular boulders, each asteroid presents a distinct silhouette against the backdrop of space. This characteristic shape, a direct consequence of their modest size, offers a visual cue to their status as remnants rather than fully formed planetary bodies. A peaceful collection of cosmic oddities, each patiently reflecting the subtle interplay of forces that shaped its individual form. Beyond their scientific value as cosmic relics, some asteroids hold a practical promise for future endeavors. Some asteroids contain valuable resources like metals and water ice. These celestial resources, locked within the rocky and icy compositions of these ancient bodies, represent a potential treasure trove for future space exploration and human expansion. Water ice, in particular, is an invaluable commodity. It can be melted for drinking, used as propellant for rockets when separated into hydrogen and oxygen, or utilized for life support systems. Metals like nickel, iron, and platinum group elements, which are rare on Earth's surface, are thought to be abundant in certain types of asteroids. The gentle extraction of these resources could eventually support long-duration missions to Mars or the establishment of orbital habitats, reducing the need to launch all materials from Earth. This quiet, potential wealth drifting through the asteroid belt offers a glimpse into a future where humanity might gently and responsibly harvest extraterrestrial resources, extending our reach into the solar system. The presence of these latent resources imbues these otherwise unassuming rocks with a profound potential, silently holding the promise of future cosmic ventures and the steady, unhurried. Among the many thousands of asteroids, one stands out as a beacon of visibility. The Vesta asteroid is bright enough to be seen from Earth with binoculars under ideal conditions. This remarkable visibility makes Vesta a unique and accessible object for amateur astronomers, offering a quiet connection to the distant asteroid belt. Vesta is the second most massive object in the asteroid belt, after the dwarf planet Ceres, and is distinguished by its relatively bright surface. Scientists believe that Vesta's surface is covered with basaltic rock, similar to the volcanic plains on Earth's moon, which reflects sunlight efficiently. Unlike many other asteroids, Vesta also shows signs of past volcanic activity and a differentiated interior, suggesting it was once a protoplanet that experienced internal heating. Its substantial size and reflective surface combine to make it a luminous point of light in the night sky, a patient, enduring presence that can be glimpsed from our own planet. This gentle visibility allows us to appreciate the subtle diversity within the asteroid belt, providing a tangible link to these ancient remnants of our solar system's formation, a quiet, luminous invitation to gaze outward and appreciate the serene complexity of our cosmic neighborhood. As we depart the tranquil, dispersed realm of the asteroid belt, our journey continues outward, leading us to the majestic presence of Jupiter, the undisputed monarch of our solar system. This colossal gas giant immediately captures attention with its most iconic and enduring feature. Jupiter's Great Red Spot is an enormous storm, wider than Earth, that has raged for at least 350 years, possibly much longer. Imagine a vast oval-shaped vortex, a serene crimson eye constantly swirling in Jupiter's southern hemisphere, a storm of such immense scale that our entire home planet could easily be swallowed within its gentle atmospheric embrace. This monumental anticyclone, observed for centuries by patient astronomers, represents a persistent, powerful atmospheric phenomenon, driven by the planet's internal heat and rapid rotation. Its continuous existence for such an extended period is a quiet testament to the enduring dynamics of Jupiter's turbulent yet stable atmosphere, where powerful currents and temperature differentials create these majestic, long-lived weather systems. The gentle, unhurried churn of this colossal storm, a silent ballet of atmospheric forces, paints a picture of a world where grand meteorological events unfold with a timeless, unwavering consistency, offering a profound glimpse into the powerful, yet serene, atmospheric processes of a gas giant. The Great Red Spot is not a fleeting tempest, but an ancient, patient force, a permanent fixture on Jupiter's ever-changing, cloud-banded face, a testament to its enduring power and the subtle, persistent nature of its atmospheric currents. Its quiet, persistent swirl reminds us of the profound timescales over which cosmic phenomena can unfold, a majestic, enduring feature that has captivated observers for generations. Jupiter's imposing presence is not merely visual, it dominates our solar system by its sheer scale. Jupiter is the largest planet in the solar system, with a mass 2.5 times greater than all other planets combined. This staggering statistic underscores its unparalleled gravitational authority and its central role in the architecture of our planetary system. Imagine gathering all the other planets, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and placing them on an immense cosmic scale. Jupiter alone would outweigh them all by a significant margin, a true giant among giants. This immense mass is predominantly composed of hydrogen and helium, remnants of the primordial cloud from which our solar system was born, gently compressed into a vast, swirling sphere under its own colossal gravity. Its profound gravitational influence extends far beyond its immediate vicinity, subtly affecting the orbits and movements of countless asteroids and comets throughout the outer solar system. This colossal size and mass make Jupiter a powerful gravitational anchor, second only to the Sun itself, orchestrating the delicate dance of its moons and shaping the paths of smaller celestial bodies. It is a quiet, dominant force, a majestic celestial body whose very existence profoundly influences the dynamics and stability of our entire cosmic neighborhood, a serene, powerful presence that commands respect. Among Jupiter's extensive retinue of 79 confirmed moons, one stands out as a prime candidate in the search for extraterrestrial life. Europa, one of Jupiter's 4 largest moons, is believed to harbor a vast subsurface ocean of liquid water, making it a prime candidate for extraterrestrial life. The evidence for this hidden ocean comes from subtle observations. The moon's fractured, icy surface, which shows signs of recent geological activity, and its weak magnetic field, which suggests the presence of a salty, conductive liquid beneath the ice. Scientists believe this ocean, potentially twice the volume of all Earth's oceans combined, is kept liquid by gentle tidal heating, a subtle warming caused by the constant gravitational tug-of-war between Europa, Jupiter, and its other large moons. This internal warmth could provide the necessary energy for chemical processes, potentially supporting microbial life in the deep, dark waters beneath the ice. The prospect of an alien ocean, shielded from the harsh radiation of space by miles of ice, presents a tantalizing possibility for astrobiological exploration. Europa floats serenely in Jupiter's immense gravitational field, a quiet, icy world holding a profound secret beneath its tranquil, frozen crust. A silent promise of potential discovery that continues to inspire wonder and scientific inquiry. Another of Jupiter's captivating large moons, Io, presents a dramatically different, yet equally active, face to the cosmos. Io, another of Jupiter's major moons, is the most volcanically active body in the solar system, constantly resurfacing itself. Unlike Europa's hidden ocean, Io's activity is expressed through a continuous, gentle outpouring of molten rock and sulfurous gases from hundreds of active volcanoes. This intense volcanism is driven by extreme tidal heating, a much more powerful version of the forces at play on Europa. Io is caught in a relentless gravitational tug-of-war between Jupiter and its other large moons, Europa and Ganymede. This constant squeezing and stretching of Io's interior generates immense frictional heat, melting its rocky interior and forcing magma to the surface. The result is a perpetually changing landscape where ancient craters are quickly buried under fresh lava flows, and towering plumes of volcanic material gently erupt into space, sometimes reaching hundreds of kilometers high. Io's vibrant, colorful surface, painted with shades of yellow, orange, and red from sulfur compounds, is a visual testament to this ceaseless geological dynamism, a world of quiet, persistent transformation. This moon is a powerful example of how gravitational forces can profoundly shape the geological evolution of a celestial body, creating a world of unhurried, yet intense, internal activity. Despite its immense size and powerful gravitational influence, Jupiter also possesses a subtle, ethereal adornment. Jupiter has a faint ring system, much less prominent than Saturn's, composed of tiny dust particles. Unlike the dazzling broad rings of its neighbor Saturn, Jupiter's rings are dark, tenuous, and composed mainly of microscopic dust grains gently shed from its inner moons as they are subtly bombarded by micrometeoroids. These delicate rings are virtually invisible from Earth without specialized telescopes and are best observed when illuminated from behind by the sun, revealing their ethereal glow. The ring system consists of 4 main components: a thick inner torus, known as the halo ring, a brighter main ring, and 2 fainter, broader outer gossamer rings, named after the moons Adrastea and Thebe, which are believed to be their source. The particles within these rings are constantly being created and dispersed, a quiet, dynamic process of replenishment and loss. Jupiter's rings offer a subtle reminder that ring systems are not exclusive to Saturn, but are a more common feature among the gas giants, each unique in its composition and visibility, a gentle, almost imperceptible whisper of cosmic dust circling the colossal planet. The sheer scale of Jupiter is closely linked to another of its defining characteristics. Jupiter's rapid rotation, completing a day in just under 10 hours, causes its distinctive flattened shape at the poles. While all planets bulge slightly at their equators due to centrifugal force from rotation, Jupiter's immense size and incredibly swift spin amplify this effect dramatically. Imagine a vast, fluid sphere spinning at such a dizzying speed that its middle gently swells outward, while its top and bottom appear slightly compressed. This subtle, yet measurable, oblateness is a direct consequence of the powerful rotational forces at play, creating a visible distortion in its otherwise perfectly spherical form. This rapid rotation also drives the powerful atmospheric currents that create Jupiter's iconic cloud bands and long-lived storms, including the Great Red Spot. The swift internal motions, combined with its gaseous composition, allow the planet to respond dynamically to these forces, creating a world that is constantly, subtly, reshaping itself with each passing rotation. It is a quiet testament to the interplay of mass, rotation, and fluid dynamics on a grand planetary scale, a majestic, unhurried spin that sculpts the very form of this gas giant. Finally, Jupiter's immense mass and powerful gravity play a crucial protective role for the inner solar system. Jupiter's immense gravity helps protect the inner solar system by deflecting or capturing comets and asteroids. Its colossal gravitational field acts as a cosmic broom, gently sweeping up or altering the trajectories of numerous smaller celestial bodies that might otherwise pose a threat to the inner rocky planets, including Earth. Many comets originating from the distant Oort cloud or Kuiper belt as they journey inward are either gently nudged onto new, safer paths by Jupiter's gravitational influence, or are captured into orbits around the gas giant itself. Some even meet their quiet end by colliding with Jupiter, leaving temporary scars on its cloud tops, a testament to its protective role. This continuous, unhurried process has been unfolding for billions of years, a silent guardianship that has profoundly shaped the environment of the inner solar system, reducing the frequency of potentially catastrophic impacts. Jupiter, the serene giant, acts as a benevolent protector, its vast gravitational presence a constant, reassuring shield, silently ensuring a more stable and tranquil existence for the worlds nestled closer to the Sun. From Jupiter's benevolent guardianship, our quiet voyage now leads us to Saturn, the breathtaking jewel of our solar system, famed for its ethereal ring system. Saturn's iconic rings are composed of billions of individual pieces of ice and rock, ranging from microscopic dust to mountain-sized chunks. Imagine a vast, shimmering halo, a celestial masterpiece woven from countless fragments, each patiently orbiting the giant planet. These countless individual particles, from the tiniest motes of cosmic dust, no larger than grains of sand, to majestic chunks of ice and rock, some as substantial as small mountains, all contribute to the ring's luminous beauty. They drift in delicate harmony, a gentle, unhurried ballet around their gas giant parent, reflecting the sun's distant light with a serene, almost otherworldly glow. This intricate composition, a grand collection of icy debris, reveals the rings not as solid structures, but as a dynamic, ever-changing tapestry of countless small worlds, each following its own precise path. The sheer number of these individual pieces, numbering in the billions, creates an illusion of breathtaking solidity from a distance. Yet up close, they reveal a profound and subtle complexity, a quiet, continuous dance of cosmic fragments that endlessly reconfigure themselves. This delicate, shimmering expanse is a testament to the patient, persistent forces that shape such grand celestial phenomena, a timeless, elegant adornment that defines Saturn's majestic presence in our cosmic neighborhood. The ceaseless, silent motion of these particles, each a tiny world unto itself, ensures the enduring brilliance of Saturn's signature feature, a testament to the elegant processes that resolve into such breathtaking beauty. Their existence speaks to an ancient, ongoing process of formation and interaction, creating a vast, shimmering disk that captivates all who gaze upon it with a sense of quiet wonder. Among Saturn's numerous companions, one moon presents a particularly intriguing mystery, a world quietly whispering secrets from its depths. Enceladus, a moon of Saturn, has geysers erupting water vapor and ice particles from its south pole, hinting at a subsurface liquid ocean. Imagine delicate, luminous plumes of icy material, gently streaming into the profound darkness of space from subtle fissures near the moon's southern regions, a constant, quiet exhalation from within its frozen shell. These persistent geysers, observed with careful precision by visiting spacecraft, are powerful indicators of an active interior, suggesting that beneath Enceladus's bright, icy crust lies a vast, tranquil reservoir of liquid water. Scientists believe this hidden ocean, potentially warmed by internal geological processes and subtle tidal heating from Saturn's immense gravitational embrace, could provide an environment conducive to the emergence of microbial life. The water vapor and ice particles, carrying traces of salts and organic molecules, are like whispering messengers from this veiled aquatic realm, offering tantalizing clues about the chemistry and potential habitability of this enigmatic moon. Enceladus orbits Saturn with serene grace, a small yet profoundly active world, its gentle eruptions a silent invitation to explore the secrets hidden beneath its tranquil, frozen exterior. This continuous, unhurried release of material into space creates a delicate, ethereal halo around the moon, a subtle signature of the deep, liquid world concealed within, revealing a quiet, persistent dynamism that profoundly shapes its interaction with the broader cosmos. The prospect of such an ocean, a tranquil liquid world shielded by miles of ice, is a source of immense wonder and careful scientific exploration, a quiet beacon in the serene search for life beyond Earth. Moving further through Saturn's system, we encounter another moon of extraordinary character, a world cloaked in a perpetual, hazy beauty. Titan, Saturn's largest moon, is the only moon in the solar system with a dense atmosphere and stable bodies of liquid on its surface, albeit liquid methane and ethane. Unlike the watery oceans of Earth or the subsurface seas of Europa and Enceladus, Titan presents a world where the familiar cycles of precipitation and evaporation involve hydrocarbons. Its thick, hazy orange atmosphere, composed primarily of nitrogen with a significant amount of methane, creates a planetary environment that resembles a primordial Earth, albeit at much colder temperatures. Through this dense atmospheric veil, patient spacecraft have peered down to discover vast, tranquil lakes and meandering rivers of liquid methane and ethane, patiently flowing across its frigid landscape. These liquid bodies, sometimes calm and reflective under the distant sunlight, sometimes gently rippled by subtle winds, form a unique hydrological cycle, complete with clouds and rain, creating a world that is eerily familiar yet profoundly alien in its elemental composition. Titan orbits Saturn as a truly distinct celestial body, a serene world unto itself, its dense atmosphere and liquid surfaces painting a picture of patient, ongoing geological and atmospheric processes. This moon stands as a testament to the diverse and surprising forms that planetary environments can take. A quiet, orange-hued world where familiar processes unfold with profoundly different materials, revealing the serene and varied possibilities of cosmic chemistry. Its unique character makes it a captivating destination for future, gentle explorations, a world that quietly holds its own secrets within its veiled, hydrocarbon-rich embrace, an enduring enigma. Returning our attention to the planet itself, Saturn holds a surprising characteristic that sets it apart from its planetary peers, a fact that speaks to its ethereal composition. Saturn is the least dense planet in our solar system. It would float if placed in a sufficiently large body of water. Imagine a bathtub vast enough to hold a planet. Saturn, with its immense gaseous composition primarily of hydrogen and helium, is so diffuse that its average density is less than that of water. This remarkable lightness, despite its enormous size, highlights its fundamentally gaseous nature. Unlike the rocky terrestrial planets, or even the denser core regions of Jupiter, Saturn's bulk is predominantly made up of the lightest elements, gently compressed but never solidifying into a heavy, compact core in the same way. This ethereal, almost weightless quality contributes to its serene appearance, its swirling cloud bands seemingly weightless as they drift across its vast expanse. This quiet fact underscores the distinct differences between the rocky inner planets and the gaseous outer giants, revealing how the materials and conditions during their formation led to such varied outcomes. Saturn's low density is a testament to the delicate balance of matter and gravity, a unique and tranquil characteristic that makes it a true anomaly among its planetary siblings. A gentle giant that defies expectations with its inherent lightness and almost imperceptible mass for its size. Further enhancing its regal status, Saturn presides over an extraordinarily numerous celestial court, a vast and diverse family of companions. Saturn has over 83 confirmed moons, the most of any planet in our solar system. This vast retinue of natural satellites, a diverse collection of icy worlds, rocky fragments, and captured celestial bodies, creates a complex and dynamic miniature system around the ringed planet. From the large geologically active moons like Titan and Enceladus, to countless smaller, irregularly shaped ice chunks and shepherd moons that sculpt the rings, each moon follows its own patient orbital path. Influenced by Saturn's immense gravitational pull and the subtle interactions with its fellow satellites. This extensive family of moons is a testament to Saturn's powerful gravitational reach, which has gently gathered and held these celestial companions in its embrace over billions of years. Each moon, in its own quiet way, contributes to the intricate gravitational dance around the planet, shaping the rings, influencing other moons, and offering unique insights into the formation and evolution of planetary systems. This teeming celestial family, constantly in motion, creates a harmonious, complex ballet, a silent and enduring testament to the rich tapestry of our solar system's outer reaches, revealing the serene and multifaceted nature of planetary companionship, a truly majestic collection of worlds. Despite their immense scale and visual prominence, Saturn's rings possess an astonishing characteristic when viewed from a different perspective, one that speaks to their delicate structure. The rings of Saturn are surprisingly thin, typically only about 20 meters thick, despite their vast diameter. Imagine a vast, ethereal disk stretching hundreds of thousands of kilometers across, wide enough to comfortably contain several Earths, or even the distance from Earth to the Moon. Yet vertically, it is no thicker than a small house or a few stories of a building. This incredible flatness is a testament to the gentle, patient gravitational forces and the countless, subtle collisions that have shaped the ring particles over billions of years, gradually settling them into a remarkably narrow plane. The constant, unhurried interactions between billions of icy fragments, each gently nudging its neighbors, have effectively ironed out any vertical irregularities, creating a structure that is almost two-dimensional in its elegant simplicity. This delicate, paper-thin veil, so breathtakingly wide, yet so remarkably shallow, underscores the intricate and subtle dynamics at play within the ring system. It is a quiet marvel of celestial mechanics, a testament to the enduring power of gentle, repetitive interactions to create a structure of such profound beauty and astonishing slenderness, a truly unique and serene feature in the cosmic landscape, a delicate whisper of cosmic architecture that continues to mesmerize. Finally, within the intricate tapestry of Saturn's rings, one prominent feature highlights the subtle gravitational ballet at play, a clear pathway carved by an unseen hand. The Cassini division, a prominent gap in Saturn's rings, is cleared by the gravitational influence of the moon Mimas. This wide, dark band, easily visible even with small telescopes from Earth, is not an empty void, but a region where ring particles are significantly sparser. Its existence is a direct result of a gentle, persistent gravitational resonance with Mimas, one of Saturn's inner moons. As Mimas orbits, its gravity subtly tugs on any ring particles that would normally occupy the Cassini division. These particles, experiencing a repeated gravitational pull at specific points in their orbits, are gradually nudged out of the region, creating a clear pathway, a serene, empty channel in the otherwise dense ring system. This elegant gravitational interaction, a quiet and patient dance between a moon and countless ring particles, beautifully illustrates how even small celestial bodies can profoundly shape the larger structures around them. The Cassini division is a visible testament to the intricate, long-term gravitational dynamics that sculpt the delicate patterns within Saturn's rings, a silent, enduring monument to the subtle, powerful forces that orchestrate the celestial ballet, revealing the profound interconnectedness of Saturn's vast and beautiful system. It is a quiet reminder that even apparent emptiness can be a result of unseen, yet powerful cosmic forces, a testament to the gentle sculpting power of gravity. As we journey beyond the magnificent rings of Saturn, our cosmic path leads us to the serene, distant realms of the ice giants, Uranus and Neptune. These two ethereal blue worlds, shrouded in cold, hazy atmospheres, hold their own unique wonders and mysteries. Uranus, in particular, presents a truly exceptional orientation in its cosmic ballet. Uranus orbits the Sun on its side, with an axial tilt of 98 degrees, possibly due to an ancient collision. Imagine a planet gently rolling through space, rather than spinning upright like a top. This profound tilt means that its poles experience incredibly long periods of continuous daylight, followed by equally prolonged stretches of complete darkness, each lasting for decades. For nearly half of its 84-year orbital period, one pole faces the Sun, bathed in its distant, steady light, while the other remains in the quiet shadow of night. Then, as it continues its patient journey, the roles subtly reverse. Scientists believe this peculiar orientation, so different from the gentle upright spins of most other planets, is the lasting legacy of a colossal yet ancient and unhurried impact with another large celestial body in the early solar system. This gentle, formative collision, occurring billions of years ago, would have subtly nudged Uranus onto its side, forever altering its rotational axis. The event, though grand in scale, would have unfolded over immense timescales, a slow reorientation that left its enduring mark. This unique axial tilt creates a world of extreme, yet predictable, seasonal variations, where the very concept of day and night unfolds in a majestic, drawn-out rhythm, a testament to the powerful shaping forces that have quietly sculpted our solar system's distant, blue-green giant. Its serene, sideways roll is a quiet anomaly, a constant reminder of the subtle, yet profound events that shape the planets into their current, distinctive forms. Further into the quiet outer reaches of our solar system, Neptune, the furthest major planet, showcases an astonishing atmospheric dynamism. Neptune boasts the fastest winds in the solar system, reaching speeds of over 2,000 kilometers per hour, or 1,200 miles per hour. Imagine atmospheric currents flowing at speeds that far exceed any hurricane or typhoon ever recorded on Earth. A relentless, powerful circulation sweeping across the entire planet. These incredible wind speeds, driven by Neptune's internal heat and rapid rotation, create a turbulent yet stable atmosphere where vast storm systems can form and persist. The planet's deep, cold interior and its gaseous composition allow for these powerful currents to develop with unhindered momentum, creating a dynamic weather system that is both awe-inspiring and profoundly serene. Despite their immense velocity, these winds contribute to the gentle, unhurried flow of Neptune's atmospheric bands, painting a picture of a world where powerful forces operate within a grand, majestic equilibrium. These rapid, sweeping currents play a crucial role in distributing heat and shaping the planet's appearance, ensuring a constant, quiet churn in its ethereal blue clouds. The sheer power of these atmospheric flows is a testament to the internal energy and fluid dynamics of this distant ice giant, a silent, powerful force shaping its character. Among Neptune's tranquil retinue of moons, one stands out with a particularly unique orbital characteristic. Triton, Neptune's largest moon, orbits in a retrograde direction, opposite to Neptune's rotation, and is likely a captured Kuiper Belt object. While most moons in our solar system orbit their parent planets in the same direction that the planet spins, Triton moves in a serene, counter-rotating path. This unusual backward orbit is a strong indicator that Triton did not form alongside Neptune from the same primordial disk of material. Instead, scientists believe that Triton was once an independent dwarf planet, slowly journeying through the distant Kuiper Belt, before being gently snared by Neptune's immense gravitational pull sometime in the distant past. This ancient, unhurried capture would have been a gradual process, subtly altering Triton's trajectory and guiding it into its current, stable, yet retrograde, orbit. The gravitational forces involved in this capture would have also generated significant internal heating within Triton, contributing to its geological activity, which includes subtle, icy geysers. Triton, with its unique backward dance, offers a quiet glimpse into the dynamic history of our solar system, a testament to the gentle gravitational forces that can reshape the destinies of celestial bodies, drawing them into new, enduring relationships within the vast, serene cosmic tapestry. Its peculiar orbit is a silent echo of a momentous, yet peaceful, past event, a constant reminder of the subtle, powerful hand of gravity. Observing Uranus from afar, its distinct coloration is one of its most recognizable features, a calm, captivating hue. Uranus's atmosphere contains methane, which absorbs red light and gives the planet its distinctive blue-green hue. The planet's upper atmosphere is rich in this simple hydrocarbon, which acts as a natural filter, gently absorbing the red and orange wavelengths of sunlight. The remaining blue and green light is then scattered back into space, creating the serene, uniform blue-green appearance that characterizes this distant world. Unlike the more complex, banded atmospheres of Jupiter and Saturn, Uranus's atmosphere appears remarkably smooth and featureless, a testament to its colder temperatures and deeper, less active cloud layers. This tranquil, consistent coloration is a direct result of its atmospheric composition, a delicate interplay of light and gas that paints the planet in soothing, cool tones. It is a quiet, visual signature of Uranus's unique atmospheric chemistry, a constant, gentle glow that defines its presence among the ice giants. This subtle interaction of light with its gaseous envelope creates a truly placid and uniform appearance, a serene expanse of blue-green that invites a sense of quiet contemplation. Neighboring Neptune, while also blue, exhibits a slightly different, more vibrant shade, a subtle distinction that reveals further atmospheric complexities. Neptune's vibrant blue color is attributed to methane in its atmosphere, absorbing red light more effectively than Uranus's atmosphere. While both ice giants owe their blue coloration to the presence of methane, Neptune's blue appears richer, deeper, and more intense. This difference is believed to be due to a slightly higher concentration of methane in Neptune's upper atmosphere, or perhaps to the presence of an unknown, additional atmospheric component that enhances the absorption of red light. This subtle difference in atmospheric chemistry creates a more profound and captivating shade of blue, a visual testament to the gentle variations that can exist even between seemingly similar planetary bodies. The deep, pervasive blue of Neptune evokes a sense of serene mystery, a world cloaked in a tranquil, almost oceanic hue that reflects its distant, cold environment. It is a quiet, yet striking visual characteristic that sets Neptune apart, painting it as a jewel of the outer solar system, its color a gentle whisper of the intricate atmospheric processes unfolding deep within its gaseous embrace. This visual elegance is a constant source of wonder, a calm, deep blue that permeates its entire visible surface. These two distant worlds share a fundamental classification that distinguishes them from their larger, more gaseous brethren. Both Uranus and Neptune are classified as ice giants, composed primarily of heavier elements like oxygen, carbon, nitrogen, and sulfur in their interiors. Unlike Jupiter and Saturn, which are predominantly made of hydrogen and helium, Uranus and Neptune possess a greater proportion of these ices, which, at the extreme pressures and temperatures deep within their interiors, exist not as solid frozen blocks, but as a superpressurized fluid slush. This unique internal composition means they have a relatively small rocky core surrounded by a vast fluid mantle of water, methane, and ammonia, often referred to as a supercritical fluid or ice layer. This distinct internal structure sets them apart from the gas giants and profoundly influences their atmospheric dynamics, magnetic fields, and overall evolution. The classification as ice giants emphasizes their unique chemical makeup, which is a gentle echo of the conditions present in the outer regions of the early solar nebula, where these heavier volatile compounds were more abundant. It is a quiet testament to the diverse pathways of planetary formation, showcasing a different kind of colossal world, one dominated by a deep, fluid ocean of exotic, dense ice that patiently defines their majestic, yet enigmatic, interiors. Finally, Neptune, like its larger neighbor Jupiter, also exhibits dynamic atmospheric phenomena, though with its own distinct rhythm. Neptune has a great dark spot, a storm similar to Jupiter's Great Red Spot, though it appears and dissipates over shorter timescales. Imagine a vast, oval-shaped atmospheric vortex, a temporary dark blemish on Neptune's vibrant blue surface, a powerful storm system swirling with high-speed winds. These immense anticyclones, akin to Jupiter's enduring Great Red Spot, are grand atmospheric features driven by the planet's internal heat and rapid rotation. However, unlike Jupiter's centuries-old storm, Neptune's great dark spots are more transient, gracefully forming, evolving, and then gently fading away over a period of several years. This more ephemeral nature suggests differences in the internal dynamics and atmospheric stability between the two ice giants. The appearance and dissipation of these dark spots are a quiet testament to the ever-changing, yet serene, atmospheric processes at play on Neptune, revealing a world of dynamic, unhurried meteorological shifts. Each spot, a temporary masterpiece of atmospheric forces, emerges and dissolves with a patient, rhythmic grace, highlighting the fluid and ever-evolving nature of this distant blue world, a testament to the subtle, powerful forces that continuously sculpt its atmospheric face. These gentle, transient storms are a captivating feature of Neptune, silently demonstrating the planet's profound atmospheric dynamism. As we journey beyond the swirling atmospheres of the ice giants, our cosmic exploration carries us into the colder, more distant reaches of our solar system. A realm populated by dwarf planets and a vast collection of icy remnants. Here, we encounter Pluto, a world that has long captured our collective imagination, yet whose true scale often surprises. Pluto is smaller than the United States, with a diameter of about 2,376 kilometers, or 1,473 miles. Imagine comparing the entire expanse of a country, stretching across a continent with its diverse landscapes and bustling cities, to the serene, icy sphere of this distant world. Pluto's modest size, while still significant for a celestial body, means it is considerably smaller than any of the major planets. Its surface, a tranquil tapestry of nitrogen ice plains, towering water ice mountains, and subtle reddish haze, unfolds over an area that would fit neatly within the boundaries of a single large nation on Earth. This quiet revelation about its true dimensions helps us to appreciate the delicate scale of this icy dwarf planet, a world that, despite its small stature, holds a profound beauty and geological complexity. Pluto drifts patiently at the edge of the familiar solar system, a small, yet captivating world that has slowly revealed its intricate features to distant probes. Its size is a testament to the diversity of celestial bodies, reminding us that even the smaller worlds can possess immense scientific interest and quiet majesty, a serene presence in the outer realms. Pluto is not alone in this distant, icy frontier. It is merely one of many objects residing in a much larger, sprawling cosmic neighborhood. The Kuiper Belt is a vast region beyond Neptune containing billions of icy bodies, remnants from the solar system's formation. Imagine a colossal, flattened disk stretching far beyond the orbit of Neptune, populated by a countless multitude of frozen worlds, from small icy pebbles to dwarf planets hundreds of kilometers across. This expansive, tranquil reservoir of ancient material represents the leftover building blocks from the early, unhurried formation of our solar system, approximately 4.6 billion years ago. These icy bodies, composed of water, methane, and ammonia ices, have remained largely undisturbed in their distant orbits, preserving the pristine conditions of the primordial solar nebula. The Kuiper Belt is a silent, frozen archive, a cosmic time capsule holding invaluable clues about the early history and composition of our planetary system. Its vastness and the sheer number of its inhabitants speak to the immense scale of the early solar system and the gentle, patient processes that shaped its distant reaches. Each icy body within this tranquil belt follows its own long, elliptical path, a quiet, enduring presence in the profound cold and darkness, a testament to the enduring nature of cosmic remnants, patiently awaiting discovery and study. The reclassification of Pluto in 2006 was a pivotal moment in our understanding of these distant worlds. Pluto was reclassified as a dwarf planet in 2006, leading to a new understanding of planetary definitions. For decades, Pluto held the esteemed title of the ninth planet, a solitary outpost at the solar system's edge. However, as astronomers discovered more and more large, icy bodies within the Kuiper Belt, some comparable in size or even larger than Pluto, the need for a clearer definition of planet became apparent. The International Astronomical Union, after careful deliberation, established 3 criteria for a celestial body to be considered a planet. It must orbit the Sun. It must be massive enough for its own gravity to pull it into a nearly round shape. and it must have cleared its orbital neighborhood of other debris. Pluto, while meeting the first two criteria, did not meet the third, as it shares its orbital path with many other Kuiper Belt objects. This gentle reclassification was not a demotion, but rather an elevation of understanding, acknowledging Pluto as the prototype of a new class of celestial bodies, dwarf planets. This subtle shift in terminology reflects a more nuanced appreciation of the diverse and complex populations of our solar system, a quiet evolution in our cosmic vocabulary. It reminds us that our scientific understanding is ever evolving, patiently refining our definitions as new discoveries gently expand our knowledge of the universe. Indeed, the discovery of other substantial bodies in the Kuiper Belt directly influenced this reclassification. Eris, another dwarf planet in the Kuiper Belt, is slightly more massive than Pluto. When Eris was discovered in 2005, its estimated size and mass, initially thought to be larger than Pluto's, presented a challenge to the existing planetary definition. This finding was a key catalyst in prompting astronomers to reevaluate what truly constitutes a planet. Eris, like Pluto, is an icy world, patiently orbiting the Sun in the distant reaches of the Kuiper Belt, far beyond Neptune. Its slightly greater mass, despite its similar composition, underscored the need for a more precise and consistent framework for classifying celestial objects. The quiet presence of Eris, subtly challenging our preconceived notions, led to a more comprehensive and inclusive understanding of the diverse populations of our solar system. It is a testament to the continuous process of scientific discovery, where new observations gently refine our models and deepen our appreciation for the vast, serene complexity of the cosmos. Eris, a distant, icy world, stands as a quiet symbol of this evolving understanding, a crucial piece in the ongoing cosmic puzzle, patiently revealing the subtle intricacies of planetary formation and classification. Among the intriguing dwarf planets of the Kuiper Belt, one exhibits a particularly distinctive form. Haumea, a dwarf planet, is notable for its elongated shape and rapid rotation, causing it to flatten. Unlike the perfectly spherical forms we often associate with celestial bodies, Haumea presents a more oblate, almost football-like appearance. This unusual shape is a direct consequence of its remarkably swift spin. Haumea completes a full rotation in just under 4 hours, making it one of the fastest rotating large objects in the solar system. This rapid, gentle pirouette creates a powerful centrifugal force that subtly stretches the dwarf planet along its equator and flattens its poles, preventing it from settling into a perfectly round shape despite its substantial mass. Scientists believe that this rapid rotation and potentially its elongated form might be the result of a past, gentle collision with another object in the early Kuiper Belt, an ancient, unhurried impact that spun it into its current, distinctive state. Haumea, with its unique and elegant form, is a quiet testament to the diverse and sometimes surprising outcomes of planetary evolution, where the interplay of gravity, rotation, and ancient impacts can sculpt celestial bodies into truly singular shapes. Its rapid, yet serene spin is a constant subtle force that maintains its elongated silhouette, a unique and captivating presence in the distant, icy reaches of our solar system. Another captivating resident of this distant realm is Makemake, a dwarf planet and one of the largest Kuiper Belt objects, known for its reddish-brown color. This subtle yet distinct hue sets Makemake apart, painting it with a unique visual signature against the backdrop of the cold, dark outer solar system. Scientists believe its reddish-brown coloration is likely due to the presence of complex organic molecules, or tholins, on its surface. These tholins are formed when ultraviolet radiation from the sun gently interacts with methane and other simple organic compounds on the dwarf planet's icy crust, slowly transforming them into more complex, reddish substances. This subtle chemical process, unfolding patiently over billions of years in the profound cold and vacuum of space, has gradually imbued Makemake with its characteristic color. It is a quiet testament to the pervasive influence of solar radiation, even at such immense distances, and the gentle, persistent chemical transformations that can occur on icy worlds. Makemake drifts serenely through the Kuiper Belt, a silent reddish beacon, its unique coloration offering clues about its surface composition and the subtle chemical evolution of distant icy bodies. Its quiet, enduring presence adds another layer of intrigue to the diverse tapestry of dwarf planets, each revealing its own gentle, unique character. Beyond the dwarf planets themselves, the Kuiper Belt holds a profound significance for understanding the origins of some of our solar system's more ephemeral visitors. The Kuiper Belt is thought to be the source of many short-period comets that visit the inner solar system. Imagine a vast icy nursery, a tranquil reservoir from which these luminous wanderers occasionally emerge. Short-period comets are those that complete an orbit around the Sun in less than 200 years, making relatively frequent visits to the inner solar system. Scientists believe that gravitational perturbations, perhaps from the subtle tug of the giant planets or gentle collisions with other Kuiper Belt objects, can occasionally nudge these icy bodies out of their stable, distant orbits. Once disturbed, they begin a slow, unhurried journey inward, gradually warming as they approach the Sun and developing their characteristic glowing comas and tails. This quiet, continuous replenishment of comets from the Kuiper Belt highlights its enduring role as a dynamic, yet serene, source of celestial visitors, offering a tangible link between the distant, frozen reaches of our solar system and the warmer, more active inner regions. It is a testament to the subtle, patient gravitational forces that orchestrate the long, graceful journeys of these icy travelers, a continuous, quiet dance across vast cosmic distances. Adding another layer of complexity to this distant realm, some Kuiper Belt objects have their own moons, such as Pluto's 5 moons, including Charon. This fascinating characteristic demonstrates that the formation of satellite systems is not exclusive to the major planets, but can also occur around smaller, icy dwarf planets. Pluto, with its remarkable family of 5 known moons, Charon, Styx, Nix, Kerberos, and Hydra, offers a particularly rich example of a dwarf planet system. Charon, Pluto's largest moon, is so substantial in size relative to Pluto that the two are often considered a binary system, orbiting a common center of mass that lies between them. The formation of these moons around Kuiper Belt objects is believed to involve similar processes to those that formed larger planetary moons, such as ancient, gentle collisions or gravitational capture events in the early solar system. These miniature satellite systems provide invaluable insights into the gravitational dynamics and evolutionary pathways of distant, icy worlds. The quiet, intricate dance of these moons around their dwarf planet parents adds a profound sense of scale and complexity to the outer solar system, revealing that even in the most distant and seemingly desolate regions, the serene ballet of celestial companionship and gravitational interaction continues to unfold with elegant precision, a testament to the diverse ways in which cosmic structures can form and evolve. From Pi, our expedition now extends even further, pushing the boundaries of what we traditionally consider our solar system into realms of profound distance and subtle influence. Here, in the outermost reaches, lies a vast spherical domain of icy remnants. The Oort cloud, the outermost region of our solar system, is thought to extend up to 100,000 astronomical units from the Sun, nearly a quarter of the way to the nearest star. To truly grasp this immense scale, consider that 1 astronomical unit, or AU, represents the average distance between Earth and the Sun, approximately 150 million kilometers, or 93 million miles. Now, multiply that by 100,000. This sprawling, ethereal shell of icy debris forms the true frontier of our planetary system, a profound expanse that defines the limits of the Sun's primary gravitational dominion. It is a region so vast and so distant that it almost touches the interstellar medium, the subtle gas and dust that permeate the space between stars. Imagine this immense, tranquil sphere, a cosmic halo surrounding our familiar inner worlds, stretching so far that the light from our sun becomes a mere faint pinprick, a distant, gentle star among countless others. Within this profound darkness, countless icy bodies drift in silent, unhurried orbits, patiently tracing paths that take thousands, even millions of years to complete. This unfathomable distance ensures a serene, almost imperceptible existence for these icy fragments, each a quiet relic from the very beginnings of our solar system, patiently suspended in the deep cosmic chill. The Oort cloud represents a truly grand and majestic boundary, a testament to the expansive reach of our sun's gentle influence, a serene transition from our home system into the vast, silent sea of interstellar space, a quiet, enduring whisper of our cosmic address. This distant, icy reservoir holds a profound significance for the occasional celestial visitors that grace our inner skies. The Oort cloud is believed to be the origin of long-period comets, taking thousands of years to orbit the Sun. Picture this immense primordial cloud as a vast spherical nursery, a tranquil haven for billions of icy bodies, each a pristine remnant cometary nuclei composed of water ice. Frozen gases and dust patiently reside in their distant orbits, largely undisturbed for billions of years. However, every so often, a subtle gravitational nudge, perhaps from a passing star or the gentle pervasive tug of the Milky Way galaxy itself, will delicately alter the trajectory of one of these icy wanderers. This gentle perturbation can cause a comet to begin an unhurried, millennia-long journey inward, gradually spiraling towards the warmth and light of our Sun. As these long-period comets make their rare and majestic appearances in the inner solar system, they offer us a fleeting, luminous glimpse into the composition of the Oort cloud and the conditions of the early solar nebula. Their incredibly elongated orbits, stretching for thousands of years, are a testament to the profound distances they traverse and the patient, unhurried pace of their cosmic dance. Each luminous visitor is a quiet messenger from the deep, dark fringes of our solar system, carrying with it the ancient story of its distant, icy home, a serene reminder of the subtle forces that guide these celestial wanderers. Yet, before we even reach the theoretical limits of the Oort cloud, our solar system is enveloped and protected by another vital, invisible structure. The heliosphere is a protective bubble of solar wind that envelops our solar system, shielding it from harmful interstellar radiation. Imagine an immense, ethereal cocoon, patiently inflated and maintained by the constant outflow of charged particles from our Sun, known as the solar wind. This gentle yet powerful stream of plasma flows outward in all directions, creating a vast magnetic bubble that extends far beyond the orbits of the planets. This pervasive, unseen shield acts as a crucial guardian, deflecting the more energetic and potentially damaging cosmic rays and interstellar gas that permeate the space between stars. Without the heliosphere's constant, tranquil embrace, our solar system would be directly exposed to the harsher environment of the galaxy, a reality that would profoundly alter the conditions for life within our planetary system. It is a testament to the Sun's enduring influence, extending its protective reach far into space, creating a serene and stable environment for its planetary family. This invisible, yet undeniably potent boundary quietly defines the true extent of the Sun's immediate atmospheric and magnetic dominion, ensuring a peaceful, sheltered journey for our entire system through the vast interstellar sea. The heliosphere is a silent, enduring testament to the subtle, yet profound, protective power of our star. The outer edge of this protective bubble forms a critical boundary, a subtle, defining line in the cosmic tapestry. The heliopause is the boundary where the solar wind meets the interstellar medium, marking the edge of the heliosphere. Visualize this not as a solid wall, but as a gentle, yet firm, invisible frontier, where the outflowing solar wind which has expanded and slowed over billions of miles, finally encounters the diffuse gas and magnetic fields of interstellar space. It is a delicate transition zone, a region where the influence of our sun's constant stellar breeze gradually fades, giving way to the subtle, pervasive presence of the wider galaxy. This quiet meeting point is a dynamic region, constantly shifting and subtly responding to the varying pressures of both the solar wind and the interstellar medium. It represents the farthest reach of the sun's direct active influence, a profound threshold that marks our solar system's gentle departure from its home star's immediate embrace into the broader, more expansive environment of our Milky Way galaxy. The heliopause is a silent, enduring testament to the boundary between two distinct cosmic domains, a serene, invisible line in the cosmic sand that separates the familiar from the truly alien, a patient, unhurried transition into the vast unknown. In a monumental achievement of human ingenuity and patience, two pioneering spacecraft have quietly traversed this profound boundary. The Voyager 1 and 2 spacecraft have both crossed the heliopause, venturing into interstellar space. Launched in the late 1970s, these two enduring probes embarked on an unhurried, decades-long journey, silently carrying instruments that meticulously measured their surroundings. After traveling for over 35 years, Voyager 1, followed later by Voyager 2, gently pierced the heliopause, sending back data that confirmed their quiet departure from the sun's direct influence. This unprecedented crossing marked humanity's first tangible foray into the true interstellar medium, the vast, serene emptiness between stars. These silent messengers, now billions of miles from Earth, continue their patient journey, drifting through the subtle currents of galactic space, powered by their enduring radioisotope thermoelectric generators. Their departure from the heliosphere was not a dramatic burst, but a gradual, subtle shift in the readings of their onboard instruments, a quiet confirmation of their passage into a new, unexplored cosmic realm. The Voyager probes stand as a testament to the enduring human spirit of exploration, patiently pushing the boundaries of our knowledge and gently extending our presence into the boundless, tranquil depths of the cosmos, carrying a quiet message of humanity's curiosity to the stars. Despite its profound influence as the origin of long-period comets, the Oort cloud remains a realm of inference rather than direct observation. The Oort cloud is too distant to be directly observed, but its existence is inferred from comet observations. Its immense distance from the Sun means that any objects within it are incredibly faint, reflecting only the most minuscule amount of sunlight, making them virtually invisible to even our most powerful telescopes. The individual icy bodies are also incredibly sparse, spread out over such a vast volume that detecting them directly is an almost insurmountable challenge. Instead, scientists patiently piece together evidence of its existence by meticulously studying the behavior and characteristics of the long-period comets that occasionally visit the inner solar system. The highly eccentric, long-period orbits of these comets, which often approach the Sun from widely varying directions and from extreme distances, strongly suggest a common, distant origin point, a vast spherical reservoir of icy material far beyond the planets. This indirect yet compelling evidence allows astronomers to construct a quiet, theoretical model of the Oort cloud, painting a picture of this unseen realm. It is a testament to the subtle art of cosmic deduction, where patient observation of visible phenomena allows us to infer the existence of hidden structures, revealing the profound yet elusive architecture of our solar system's farthest reaches. A silent, enduring mystery that continues to inspire careful scientific inquiry. From the inferred, distant expanses of the Oort cloud, our attention now gently shifts to the more ephemeral, yet equally captivating, minor bodies that gracefully traverse our solar system: comets, meteors, and cosmic dust. These celestial wanderers, though often small, play significant roles in the cosmic tapestry. Comets are icy bodies that release gas and dust as they approach the sun, forming a glowing coma and a tail. Imagine a pristine, frozen nucleus, perhaps only a few kilometers across, patiently journeying through the profound cold of the outer solar system for millennia. As this icy traveler gradually nears the sun's gentle warmth, the frozen gases within its core begin to subtly sublimate, transforming directly from solid ice into gas without passing through a liquid phase. This escaping gas, carrying with it tiny particles of dust, forms a diffuse, luminous cloud around the nucleus, known as the coma, which can stretch for hundreds of thousands of kilometers. The gentle pressure of the solar wind and the sun's radiation then push this liberated gas and dust away from the sun, creating the comet's iconic, ethereal tail, often stretching for millions of kilometers across the silent vacuum of space. This luminous display, a transient yet majestic spectacle, is a beautiful testament to the subtle power of solar energy, transforming a cold, dark chunk of ice into a radiant, celestial beacon. Each comet, in its unhurried approach and departure, offers a fleeting, quiet moment of cosmic beauty, a silent, enduring dance of ice and light that captivates observers on Earth, revealing the delicate, yet profound, transformation that solar warmth can bring to these ancient, icy visitors. These luminous cosmic visitors leave behind a subtle, yet profound legacy that Earth occasionally encounters. Meteor showers occur when Earth passes through trails of dust and debris left behind by comets. As a comet gracefully orbits the sun, it continuously sheds tiny particles of dust and rocky fragments, gently dispersing them along its orbital path. These trails of cosmic debris, like invisible ribbons stretching across space, patiently remain in place long after the comet has moved on. When Earth, in its own unhurried journey around the sun, intersects one of these ancient dust trails, the countless small particles enter our atmosphere. Each tiny fragment, encountering the friction of Earth's upper atmosphere, gently heats up and vaporizes, creating a brief, luminous streak of light across the night sky. These fleeting celestial streaks, often referred to as shooting stars, appear in great numbers, creating a mesmerizing display of cosmic fireworks. The predictable timing of these meteor showers allows astronomers to patiently anticipate their arrival, offering a quiet, recurring spectacle that links our planet directly to the distant, ethereal journeys of comets. It is a testament to the enduring presence of cosmic dust and the gentle, unhurried intersection of celestial paths. A beautiful, silent reminder of the constant, subtle exchange of matter within our solar system. Each luminous streak is a quiet whisper from a distant comet, a fleeting moment of cosmic connection. To understand these luminous streaks fully, it's helpful to clarify the subtle distinctions in terminology. A meteoroid is a small piece of rock or metal in space, while a meteor is the streak of light it makes as it burns up in Earth's atmosphere. Imagine a tiny, unassuming fragment, perhaps no larger than a grain of sand or a small pebble, quietly drifting through the vast emptiness of interstellar space. This is a meteoroid, a silent wanderer, a remnant of a comet or asteroid, patiently following its cosmic trajectory. When this small piece of cosmic debris gently encounters Earth's atmosphere, the intense friction causes it to heat rapidly, glowing brightly as it vaporizes. This luminous phenomenon, the fleeting flash of light that graces our night sky, is what we call a meteor. The meteoroid itself is often completely consumed by this gentle atmospheric friction, leaving no trace behind. This distinction emphasizes the different stages of a celestial object's journey, its silent existence in space, its fiery yet brief passage through our atmospheric veil, and its potential, though rare, arrival on our planet's surface. It is a subtle, yet precise way of describing the celestial dance that unfolds above us. A quiet recognition of the transformation from a dark, unseen particle to a momentary, luminous spectacle, a testament to the gentle, yet effective protection offered by our planet's atmospheric shield. and for those rare instances when these cosmic travelers endure their fiery descent. A meteorite is a meteoroid that survives its passage through the atmosphere and lands on Earth's surface. While most meteoroids are small and completely vaporized by the friction of Earth's atmosphere, larger or more robust pieces can withstand the intense heat and pressure of entry. These resilient fragments, having endured a gentle yet profound transformation during their journey, slowly decelerate as they fall through the lower atmosphere, eventually settling softly upon the Earth's surface. Once they come to rest, they are no longer called meteoroids or meteors, but meteorites, tangible pieces of extraterrestrial material that offer us a direct, quiet connection to the wider solar system. These precious cosmic samples, often dark and irregularly shaped, carry within them invaluable scientific information about the composition of asteroids, comets. Each meteorite is a silent messenger, a patiently delivered piece of cosmic history, offering scientists a unique opportunity to study primordial matter without the need for expensive space missions. Their quiet arrival on Earth's surface is a testament to their enduring journey through space and atmosphere, a gentle gift from the cosmos, patiently awaiting discovery and study, providing a tangible link to the vast, serene universe beyond our world. Adding to the constant cosmic influx, our planet is perpetually bathed in a subtle, almost imperceptible rain of extraterrestrial material. Cosmic dust, microscopic particles from asteroids and comets, constantly rains down on Earth. Imagine countless tiny motes, each no larger than a grain of pollen or a microscopic speck, gently drifting through space, remnants of ancient asteroids and the ethereal tails of passing comets. These minute fragments, shed from larger celestial bodies over billions of years, are pervasive throughout our solar system. As Earth patiently orbits the Sun, it continuously sweeps up vast quantities of this cosmic dust. Each tiny particle, encountering our planet's atmosphere, gently floats downward, eventually settling onto surfaces across the globe. While individually imperceptible, the cumulative amount of cosmic dust reaching Earth each year is substantial, estimated to be many tons. This constant, unhurried shower of extraterrestrial material is a silent, enduring connection between our planet and the wider cosmos, a gentle reminder that Earth is an integral part of a larger, dynamic system. This quiet, ceaseless influx of dust contributes subtly to our planet's geology and atmosphere, a testament to the ongoing, gentle exchange of matter within our solar system, a pervasive, yet tranquil, cosmic precipitation that has been unfolding for eons. Beyond their physical composition, some of these cosmic visitors carry a profound chemical significance. Some meteorites contain organic molecules, offering clues about the building blocks of life. When certain types of meteorites, particularly carbonaceous chondrites, are carefully analyzed by scientists, they reveal the presence of complex organic compounds, including amino acids, which are the fundamental components of proteins. These molecules are not evidence of life itself originating in space, but rather suggest that the raw chemical ingredients necessary for life's emergence were readily available and widely distributed throughout the early solar system. It is believed that these organic molecules formed patiently in the cold, dark reaches of space, perhaps within the primordial solar nebula or on the surfaces of asteroids, slowly synthesizing over vast stretches of cosmic time. Their quiet delivery to early Earth via meteorite impacts could have provided a crucial supply of these vital building blocks, gently seeding our planet with the raw materials needed for life to begin its intricate journey. This profound discovery links the gentle arrival of meteorites to the very origins of life on Earth, suggesting a deep interconnectedness between cosmic chemistry and terrestrial biology. Each meteorite, a silent, unassuming rock, holds within it a quiet, enduring whisper of life's potential, a testament to the pervasive presence of organic chemistry in the serene expanse of the universe. Finally, we return to the majestic comets themselves to appreciate the delicate balance of their structure and the immense scale of their luminous displays. The nucleus of a comet is typically only a few kilometers across, but its tail can stretch for millions of kilometers. Imagine a small, dark, icy nucleus, perhaps the size of a mountain or a small city, quietly drifting through space. This relatively modest core, a frozen reservoir of primordial material, holds the potential for truly spectacular cosmic artistry. As the comet gently approaches the Sun, the nucleus awakens, releasing gas and dust that form its brilliant coma, and, most strikingly, its expansive tail. This ethereal tail, a luminous streamer of gas and dust, can extend for an astonishing distance, often spanning tens of millions of kilometers, sometimes even reaching the distance from Earth to the Sun. This immense, graceful appendage is a testament to the subtle yet powerful forces of the solar wind and radiation pressure, which gently sweep the liberated material away from the comet's nucleus, creating a visually breathtaking, yet incredibly diffuse, structure. The immense scale of the tail, compared to the tiny nucleus, highlights the profound transformation that occurs as a comet responds to the Sun's distant warmth. It is a quiet, majestic display of cosmic interaction, a silent, luminous brushstroke across the canvas of space, revealing the delicate yet far-reaching beauty of these icy wanderers, a constant source of quiet wonder in our tranquil solar system. As we gently conclude our observations of the solar system's minor bodies, our journey now takes us back in time to the very genesis of our cosmic home, exploring the profound processes of solar system formation and its early history. Our solar system formed approximately 4.57 billion years ago from a giant rotating cloud of gas and dust known as the solar nebula. Imagine an immense, swirling expanse of cosmic material, a vast ethereal cloud of hydrogen, helium, and tiny particles of dust, patiently drifting through the interstellar medium. This primordial nebula, cold and diffuse, began its slow, unhurried transformation under the subtle influence of gravity. Perhaps a distant supernova, a gentle burst of radiance from a dying star, sent a subtle shockwave through space, causing a portion of this nebula to gently compress. As it slowly collapsed inward, the cloud began to rotate, gradually flattening into a vast, spinning disk, much like a cosmic pancake. This majestic, unhurried process, unfolding over millions of years, laid the fundamental groundwork for everything we observe in our solar system today. The solar nebula was a serene, fertile cradle, patiently nurturing the birth of our Sun and its accompanying planetary family. This ancient formative period is a testament to the elegant, self-organizing power of gravity and the abundance of cosmic raw materials, a quiet, profound beginning to our planetary story, a gentle unfolding of matter and energy that would eventually lead to the vibrant, complex system we call home. The subtle, pervasive forces within this initial cloud were the sculptors of our cosmic destiny, patiently shaping the fundamental architecture of our stellar neighborhood. Within this slowly rotating solar nebula, a crucial boundary emerged, subtly dictating the very nature of the worlds that would form. The frost line, or snow line, in the early solar nebula dictated where rocky planets, forming closer to the Sun, and gas or ice giants, forming in the colder, outer regions, would take shape. Imagine a specific distance from the nascent Sun within this swirling disk, a gentle demarcation where temperatures dropped sufficiently for volatile compounds like water, methane, and ammonia to condense into solid ice grains. Inside this frost line, where temperatures remained higher, these icy materials would have been vaporized, leaving only heavier, rocky, and metallic elements to coalesce. This subtle thermal gradient, a quiet dividing line, led to the formation of the dense, terrestrial planets, Mercury, Venus, Earth, and Mars, composed predominantly of rock and metal. Beyond the frost line, however, the abundance of solid ice grains provided much more material for accretion. Here, the nascent cores of the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, could rapidly grow to immense sizes, drawing in vast envelopes of hydrogen and helium gas. This elegant, natural separation, a testament to the subtle interplay of temperature and chemistry, profoundly shaped the fundamental composition and character of the planets, creating the distinct inner rocky worlds and outer gaseous and icy giants we observe today. It was a gentle, yet absolute, cosmic zoning, patiently guiding the evolution of our planetary family. The early solar system, while slowly coalescing, was a remarkably dynamic environment. The early solar system was a turbulent place, with frequent collisions among planetesimals, the building blocks of planets. Imagine countless small, rocky and icy bodies, ranging from meters to hundreds of kilometers in size, patiently orbiting the nascent sun. These planetesimals, the direct descendants of the dust and grit within the solar nebula, were engaged in a continuous, unhurried dance of gravitational attraction and occasional, gentle impacts. While some collisions were destructive, breaking apart smaller bodies, many were constructive, leading to the gradual accumulation of mass. Over millions of years, these repeated, subtle encounters allowed planetesimals to gently accrete or stick together, slowly growing larger and larger. This process, known as accretion, was the primary mechanism by which the planets themselves were slowly assembled, piece by piece, from this primordial debris. The turbulence was not chaotic in a violent sense, but a persistent, gentle interaction that gradually sorted and combined the raw materials of our solar system. This era of frequent, yet formative, collisions was a critical stage in planetary formation, a testament to the slow, patient processes by which vast celestial bodies are meticulously built from countless smaller fragments, a quiet, intricate construction project unfolding across the immense canvas of space. Each gentle impact contributed to the majestic growth of the planets, shaping their very foundations. At the very heart of this nascent system, the Sun itself was undergoing its own profound transformation. The Sun's formation began when the densest part of the solar nebula collapsed under its own gravity, heating up and igniting fusion. Within the swirling disk of the solar nebula, gravitational forces gradually pulled the vast majority of the gas and dust towards the center. As this central region slowly accumulated more and more mass, its gravitational pull intensified, causing it to contract further. This gentle inward collapse generated immense pressure and friction, which in turn caused the temperature at the core of this growing protostar to steadily rise. For millions of years, this central mass continued to grow hotter and denser, until the conditions within its core reached the critical threshold of 15 million degrees Celsius. At this precise moment, under unimaginable pressure, nuclear fusion gently ignited, transforming hydrogen into helium and releasing a prodigious amount of energy. This serene, yet monumental event marked the birth of our star, a quiet awakening that brought light and warmth to the nascent solar system. The ignition of fusion transformed the protostar into a true star, a stable and luminous source of energy that would sustain its planetary family for billions of years. It was a gentle, yet powerful birth, a silent promise of enduring radiance that profoundly shaped the destiny of our entire cosmic neighborhood, patiently illuminating its vast expanse. Following the Sun's gentle ignition, the remaining scattered fragments in the solar nebula continued their patient assembly. Planetesimals gradually accreted or stuck together to form larger protoplanets. Imagine the countless planetesimals, those small, rocky and icy building blocks, gently orbiting the newly formed Sun. Through a combination of gravitational attraction and subtle, slow-motion collisions, these smaller bodies began to stick together. This process, often described as a cosmic snowball effect, was not instantaneous or dramatic, but a gradual, unhurried accumulation of material. As planetesimals gently bumped into each other, they would often merge, slowly increasing their mass and thus their gravitational pull. This enhanced gravity then allowed them to attract even more surrounding material, growing larger and larger over millions of years. These growing bodies, now substantial enough to exert significant gravitational influence, became known as protoplanets, the embryonic forms of the planets we know today. This slow, patient process of accretion, driven by the fundamental force of gravity, was the primary mechanism by which the diverse worlds of our solar system were meticulously constructed from the primordial debris. It was a gentle, yet persistent, act of cosmic construction, where countless small pieces patiently combined to form the majestic, rounded forms of the planets, a silent testament to the enduring power of growth and coalescence in the early solar system. However, the early solar system was not always a picture of calm, continuous growth. It also experienced periods of more intense, though still unhurried activity. The late heavy bombardment was a period about 3.8 billion years ago, when the inner solar system experienced an unusually high number of asteroid and comet impacts. Imagine a time after the initial planet formation, when the inner planets had largely settled into their orbits, but residual populations of asteroids and comets, subtly perturbed by the gravitational migration of the giant planets, were gently scattered inward. This increased influx of smaller bodies led to a prolonged era of heightened impacts, though still spread across millions of years, leaving countless craters on the surfaces of the Moon, Mercury, and Mars. Earth, too, would have experienced this bombardment, though geological activity and erosion have long since erased most of the evidence. This period, while marked by a greater frequency of impacts, was still a gradual, unhurried process on cosmic timescales, a gentle redistribution of leftover material rather than a sudden, catastrophic event. The late heavy bombardment is a testament to the dynamic, evolving nature of the early solar system, a period where the orbits of countless small bodies were gently reshaped, leading to a profound, yet patient, sculpting of the inner planet's surfaces. It serves as a quiet reminder of the ongoing interactions that shape and refine planetary environments, a subtle, ancient echo of cosmic restlessness. Finally, the fundamental building blocks of our solar system reflect its ancient origins. The chemical composition of the solar system is primarily hydrogen and helium, inherited from the solar nebula. These two lightest elements, formed in the earliest moments of the universe during the Big Bang, constituted the vast majority of the primordial gas and dust cloud from which our sun and planets were born. Hydrogen, the most abundant element, fuels the sun's nuclear fusion, while helium is its primary product. Even though the terrestrial planets are rich in heavier elements like iron, silicon, and oxygen, and the gas giants contain other ices, the overwhelming bulk of the solar system's total mass, dominated by the sun, is still composed of these two fundamental elements. This pervasive presence of hydrogen and helium is a direct, quiet link to the universe's earliest moments, a testament to the primordial soup from which all celestial bodies eventually coalesced. It is a serene reminder that our solar system, with all its intricate complexity and diversity, is ultimately built from the simplest and most abundant ingredients in the cosmos. This fundamental chemical signature, patiently preserved throughout our system, underscores the deep, enduring connection between our local cosmic neighborhood and the grand, universal tapestry of matter and energy. From the primordial chemical signatures that define our solar system's origins, we now turn our attention to some of the unique phenomena and precise measurements that reveal the intricate workings of our cosmic neighborhood. One such elegant interaction is observed in the gravitational ballet of celestial bodies. Orbital resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other, like some of Jupiter's moons. Imagine a delicate, rhythmic dance performed by celestial partners, where their orbital periods are in a simple, harmonious ratio. For instance, among Jupiter's Galilean moons, Io, Europa, and Ganymede are locked in a beautiful 1:2 to 4 orbital resonance. This means that for every one orbit of Ganymede, Europa completes exactly 2 orbits, and Io completes precisely 4. This consistent, periodic gravitational tug prevents the moons from settling into perfectly circular paths, subtly stretching and squeezing their interiors. This gentle, yet persistent, tidal stress generates internal heat, which is responsible for the intense volcanism on Io and the subsurface liquid ocean on Europa. Orbital resonance is a testament to the long-term gravitational interactions that shape planetary systems, a quiet, enduring rhythm that governs the movements and even the internal geology of celestial bodies. It is a subtle, yet powerful manifestation of cosmic harmony, revealing how the patient, unhurried dance of gravity can create profound and lasting effects throughout our solar system. This elegant interplay of forces illustrates the deep, interconnected nature of celestial mechanics, a serene and continuous ballet that defines these distant worlds. At the very foundation of how we perceive and measure these cosmic phenomena lies a fundamental constant of the universe. The speed of light is the fastest known speed in the universe. This incredible velocity, an ultimate cosmic speed limit, is not merely a rapid movement, but a fundamental property of the fabric of space-time itself. Nothing with mass can ever reach or exceed this speed, making light the fastest messenger across the vast, silent expanses of the cosmos. This constant, unwavering speed allows light to traverse immense distances, carrying information from distant stars and galaxies to our telescopes and indeed to our very eyes. It is a quiet, profound truth that shapes our understanding of cosmic distances and the nature of time in the universe. The serene, unhindered journey of light, always at this ultimate speed, ensures that every observation we make of a celestial object is a glimpse into its past. This universal speed limit is a testament to the elegant, unchanging laws that govern our universe, a silent, enduring constant in the ever-unfolding cosmic drama, a fundamental principle that underpins all our attempts to measure and comprehend the vastness around us. This inherent delay in light's journey has a fascinating consequence for our cosmic observations. Observing distant objects in the solar system allows us to look back in time, as their light takes time to reach us. When we gaze upon the majestic rings of Saturn, or the cloud-banded face of Jupiter, or even the subtle reddish hue of Mars, we are not seeing them exactly as they are at this very instant. Instead, we are witnessing them as they appeared minutes or even hours ago. For instance, light from Jupiter takes about 33 to 53 minutes to reach Earth, depending on our planet's positions. Light from Saturn takes over an hour. This cosmic time delay is a gentle reminder of the vast distances involved, turning our telescopes into quiet, patient time machines. Each photon that enters our eye or our instrument carries with it a snapshot of the past, allowing astronomers to study the evolution of planetary features, track the movements of moons, and monitor the subtle changes in distant atmospheres. It is a profound yet serene aspect of cosmic observation, where the very act of looking outward is also a journey backward through time, revealing the ongoing story of our solar system's gentle, unhurried evolution. This quiet, temporal dimension adds a layer of depth to every celestial view, offering a unique perspective on the dynamic history of our cosmic neighborhood. Furthermore, our entire solar system is not a fixed, static entity, but a dynamic traveler within a much grander structure. The solar system is not static, but is constantly moving through the Milky Way galaxy. Imagine our sun, with its retinue of planets, asteroids, and comets, patiently orbiting the galactic center, completing one full revolution roughly every 250 million years. This immense, unhurried journey carries us through the spiral arms of our home galaxy, a vast, majestic dance through a sea of billions of stars, gas, and dust. As we travel, our solar system gently bobs up and down and oscillates inward and outward relative to the galactic plane, a subtle, rhythmic motion within the galaxy's gravitational embrace. This continuous silent movement means that our cosmic neighborhood is constantly encountering new regions of interstellar space, subtly influencing the environment around us. It is a profound, yet serene realization that our entire planetary home is a single, cohesive unit, gracefully navigating the immense, complex architecture of the Milky Way. This constant, unhurried galactic voyage underscores the dynamic nature of the cosmos, a testament to the grand, pervasive gravitational forces that orchestrate the movements of stars and planetary systems on truly monumental scales. As we ponder the potential for life beyond Earth, a vital concept guides our search. The concept of a habitable zone defines the region around a star where conditions might allow for liquid water on a planet's surface. Imagine a gentle, orbital sweet spot around any given star. A specific range of distances where a planet could maintain temperatures suitable for water to exist in its liquid state. This Goldilocks zone is neither too close to the star, where water would quickly boil away, nor too far, where it would perpetually freeze solid. The presence of liquid water is considered a fundamental requirement for life as we understand it, making this zone a crucial focus for astrobiologists. The size and location of a star's habitable zone depend on its size and luminosity. Hotter, more luminous stars have wider, more distant habitable zones, while cooler, dimmer stars have narrower, closer zones. Earth, orbiting within our Sun's habitable zone, is a prime example of a world where conditions have allowed liquid water, and thus life, to flourish for billions of years. This quiet, theoretical boundary provides a serene framework for our search for exoplanets that might harbor life, a gentle guide in the vast cosmic quest for other habitable worlds, patiently reminding us of the delicate balance required for life's emergence. Yet, even our life-giving Sun, in its serene constancy, exhibits dynamic behaviors that can subtly influence our planetary home. The Sun's activity, like solar flares and coronal mass ejections, can impact Earth's technology and auroras. Imagine sudden, gentle bursts of intense radiation or vast, slow clouds of magnetized plasma gently erupting from the Sun's surface, slowly propagating through space. These solar phenomena, while a natural part of our star's 11-year activity cycle, can interact with Earth's magnetic field and atmosphere. Solar flares release powerful bursts of X-rays and ultraviolet radiation that can subtly disrupt radio communications and satellite signals. Coronal mass ejections, or CMEs, release colossal bubbles of charged particles that, upon reaching Earth, can induce geomagnetic storms. These storms, while not physically harmful on the surface, can cause gentle fluctuations in power grids and subtly interfere with satellite operations. However, a more beautiful consequence of these solar events is the creation of the auroras, the mesmerizing northern and southern lights, as charged particles gently interact with Earth's atmospheric gases near the poles. This delicate interplay between the Sun's dynamic processes and Earth's protective magnetic field is a testament to the profound interconnectedness of our solar system. A quiet reminder that even our distant star actively, yet gently, shapes the environment of our home planet, creating both subtle challenges and breathtaking celestial displays. Finally, a familiar and fundamental characteristic of our own planet dictates the very rhythm of our lives. The tilt of Earth's axis is responsible for our seasons, as different parts of the planet receive more direct sunlight throughout the year. Imagine Earth gracefully orbiting the Sun, not perfectly upright, but with its rotational axis gently tilted at an angle of approximately 23.5 degrees relative to its orbital plane. This constant, unwavering tilt means that as Earth makes its unhurried journey around the Sun, different hemispheres are alternately angled towards or away from our star. When the northern hemisphere is tilted towards the Sun, it receives more direct and concentrated sunlight, leading to warmer temperatures and longer days, our summer. 6 months later, as Earth continues its patient orbit, the northern hemisphere is tilted away from the Sun, receiving less direct sunlight, resulting in cooler temperatures and shorter days, our winter. The southern hemisphere experiences the opposite seasons at these times. This elegant, predictable axial tilt is the primary driver of our planet's seasonal cycle, a gentle, rhythmic variation that profoundly influences climate, ecosystems, and human activity. It is a testament to the enduring stability of Earth's orientation in space, a quiet, celestial mechanism that ensures the regular, unhurried progression of our seasons, painting our world in a continuous, beautiful cycle of change and renewal, a fundamental aspect of Earth's serene, life-sustaining environment. From the gentle, rhythmic progression of Earth's seasons, our thoughts now turn to humanity's profound quest for understanding life beyond our home world, and to the deep future that patiently awaits our solar system. In this serene exploration, some celestial bodies stand out with particular promise. Beyond Earth, moons like Europa and Enceladus are considered the most promising places in our solar system to find extraterrestrial life due to their subsurface oceans. These two icy satellites, Europa orbiting the colossal Jupiter and Enceladus circling the ringed Saturn, are both cloaked in thick, brilliant shells of water ice. Yet, beneath these frozen exteriors, scientists believe vast, tranquil oceans of liquid water lie hidden, shielded from the harsh radiation of space. On Europa, observations of its fractured surface, which shows signs of subtle geological activity and dynamic ice tectonics, along with magnetic field measurements, strongly suggest the presence of this deep, liquid realm. Similarly, Enceladus actively vents plumes of quiet geysers that serve as direct evidence of a subsurface reservoir, gently exhaling its secrets into the vacuum. The presence of liquid water, a fundamental requirement for life as we know it, makes these moons incredibly compelling candidates in the patient search for microbial life beyond Earth. They float serenely in the outer solar system, two distant icy worlds holding the profound quiet promise of alien oceans and the potential for life to have found a way to flourish in the profound depths. Far from the direct warmth of the sun, their existence expands our understanding of where life might emerge, pushing the boundaries of the habitable zone to include worlds warmed not by direct starlight, but by internal subtle forces. This quiet potential illuminates these moons as beacons of hope in the grand cosmic quest, inviting future, gentle explorations to uncover their hidden aquatic wonders. The secret to these hidden liquid worlds lies in a subtle yet powerful cosmic mechanism. Tidal heating, caused by gravitational interactions with larger planets, keeps the subsurface oceans of some moons liquid. Imagine a delicate, continuous tug-of-war unfolding between a moon and its massive parent planet. As Europa and Enceladus orbit their respective gas giants, Jupiter and Saturn, they are subjected to immense, varying gravitational forces. These forces gently stretch and compress the moon's interiors, subtly deforming their rocky cores and icy mantles. This constant, gentle squeezing and releasing generates internal friction, which in turn produces a steady, persistent warmth deep within their structures. This internally generated heat, much like the gentle flexing of a material, is sufficient to melt vast quantities of ice, creating and sustaining the subsurface liquid oceans, even in the frigid environment of the outer solar system. The closer a moon orbits its giant planet, and the more elliptical its orbit, the stronger these tidal forces become, leading to more intense internal heating. This elegant process of gravitational energy conversion ensures that these distant oceans remain in a liquid state, providing a stable environment where complex chemistry and potentially life could patiently develop over billions of years. It is a testament to the pervasive, subtle power of gravity, not just as a force that shapes orbits, but also as a quiet, internal furnace that nurtures the possibility of life in unexpected corners of our cosmic neighborhood. A gentle, enduring warmth, sustaining liquid realms in the profound cold. As we peer into the distant future, the ultimate fate of our sun, and by extension, our solar system, unfolds in a series of grand, unhurried stellar transformations. In about 5 billion years, the sun will expand into a red giant, likely engulfing Mercury, Venus, and possibly Earth. This profound change is a natural and inevitable stage in the life cycle of a star like our Sun. As its core gradually depletes its hydrogen fuel, it will begin to fuse helium, causing its outer layers to gently swell outward, cooling as they expand. This slow, majestic expansion will transform our familiar yellow dwarf into a colossal red giant, its luminous surface growing to an immense size. Mercury and Venus, being the innermost planets, will undoubtedly be absorbed into the Sun's vast, expanding envelope, gently melting away into its fiery embrace. For Earth, the fate is less certain, but still profoundly significant. While some models suggest Earth might just escape outright engulfment, its oceans will boil away, and its surface will become irrevocably scorched by the Sun's immense heat and proximity. This unhurried, gentle swelling of our star marks the end of its main sequence stability, transforming our once habitable zone into a searing inferno. It is a testament to the patient, predictable evolution of stars, a quiet, inevitable cosmic destiny that will slowly, elegantly reshape the inner architecture of our solar system, a profound yet serene transition from a life-giving star to a sprawling, cooler giant. Following this immense expansion, our Sun will undergo another serene yet dramatic transformation. After its red giant phase, the Sun will shed its outer layers, forming a planetary nebula, and its core will become a white dwarf star. Imagine the Sun's vast, expanded outer atmosphere gently detaching and drifting away into space, creating an ethereal, luminous shell of gas and dust. This beautiful iridescent cloud, known as a planetary nebula, will slowly expand and dissipate over tens of thousands of years, painting the cosmos with its vibrant, transient beauty. This gentle exhalation of material will leave behind the Sun's dense, compact core, a quiet remnant known as a white dwarf. This white dwarf will be roughly the size of Earth, but with a mass comparable to the original Sun, making it incredibly dense. It will be a slowly cooling cosmic ember, radiating its remaining stored heat into space for trillions of years, a patient, enduring testament to the star it once was. This final graceful act of stellar evolution marks the Sun's transformation from a luminous giant into a silent, compact, stellar corpse. It is a profound, yet serene, celestial farewell, a quiet return of its constituent elements to the cosmos, gently enriching the interstellar medium for future generations of stars and planets, a patient, unhurried conclusion to its active stellar life. Our current location within the vast expanse of the Milky Way galaxy offers a subtle advantage for the long-term stability of life. The solar system is located far from the galactic center, in a quieter region of the Milky Way, which may be beneficial for life. Imagine our galaxy as a colossal, swirling city of stars, with a bustling, densely packed downtown at its core. The galactic center is a region of intense activity, filled with supermassive black holes, frequent supernovae, and dense clusters of stars, all contributing to a more turbulent and energetic environment. Our solar system, however, resides in one of the Milky Way's quieter spiral arms, approximately 27,000 light-years from the bustling galactic core. This more serene location offers a protective distance from the potentially disruptive forces and high-energy radiation that are more prevalent in the central regions. The calmer environment allows for a more stable and prolonged period of planetary evolution and the gentle emergence of complex life, free from frequent catastrophic cosmic events. It is a testament to the fortunate positioning of our cosmic home, a quiet, enduring haven in the vast, dynamic tapestry of our galaxy. This tranquil placement ensures a long, unhurried period of cosmic calm, fostering the conditions necessary for life to patiently thrive, a subtle yet profound benefit for our habitable world. In our ongoing quest to understand life's presence in the universe, scientists are diligently and patiently searching for subtle clues. Scientists are actively searching for biosignatures, indicators of past or present life on other solar system bodies. This meticulous search involves deploying sophisticated spacecraft and instruments to analyze the atmospheres, surfaces, and subsurface environments of promising worlds such as Mars, Europa, and Enceladus. Biosignatures can take many forms: specific chemical compounds or combinations of molecules that are typically produced by biological processes, unusual isotopic ratios that suggest biological activity, or even complex organic molecules that are the building blocks of life. For instance, the detection of methane in Mars' atmosphere, while not conclusive, is a subtle hint that warrants further investigation. The careful analysis of samples returned from other bodies or in situ measurements by robotic landers offers the best chance to identify these elusive indicators. This patient, unhurried scientific endeavor is driven by a deep curiosity about our place in the cosmos, a gentle yet persistent effort to uncover whether life has emerged elsewhere in our immediate cosmic neighborhood. It is a testament to humanity's enduring spirit of inquiry, a quiet, systematic search for the subtle whispers of life beyond Earth, patiently expanding our understanding of biology's reach. Ultimately, as cosmic time continues its unhurried flow, the grand narrative of our solar system will reach its final, serene chapter. The ultimate fate of the solar system is to slowly disperse as the sun becomes a white dwarf and planets eventually drift away or are ejected. After our sun completes its luminous life cycle and transforms into a cooling white dwarf, its gravitational influence on the remaining planets will subtly diminish as it loses a significant portion of its mass during the planetary nebula phase. This gentle weakening of its gravitational tether will cause the remaining outer planets, now orbiting a much smaller, denser star, to gradually drift into wider and wider orbits. Over truly immense timescales, spanning trillions of years, the gravitational perturbations from passing stars in the galaxy, though rare, will become increasingly effective at subtly nudging these planets. These gentle gravitational interactions could eventually cause some planets to be slowly ejected from the solar system entirely, sending them on solitary journeys through interstellar space. Others might remain bound to the white dwarf, but in profoundly altered, distant orbits. This final, unhurried dispersal is not a violent end, but a slow, elegant unbinding, a gradual fading of our planetary family into the vastness of the cosmos. It is a serene, patient conclusion to a billions of years-long story, a testament to the enduring, subtle forces of gravity and the pervasive, unhurried rhythm of cosmic change, as our solar system gently dissolves back into the grand tapestry of the universe. From the which, we now lift our gaze to see where our entire solar system resides within that magnificent, sprawling design. Our solar system is part of the Orion arm of the Milky Way galaxy, one of its spiral arms. Imagine, if you will, our home galaxy, the Milky Way, as a colossal flat disk of billions upon billions of stars, vast clouds of gas and delicate cosmic dust, all slowly turning with an immense, unhurried grace in the profound silence of space. From a distant vantage point, it would unfurl before our eyes as a luminous, majestic pinwheel with elegant, curving spiral arms extending outward from a brilliant, densely packed central bulge. Our own sun, with its accompanying retinue of planets, dwarf planets, asteroids, and comets, resides nestled gently within one of these ethereal, luminous arms. Specifically, we are located in what astronomers refer to as the Orion Arm, which is sometimes also known as the local arm due to our presence within it. This particular spiral arm is not one of the Milky Way's largest or most dramatically prominent, but rather a more subtle, meandering offshoot, a quiet, flowing current of stars and nebulae situated patiently between two of the galaxy's more substantial and visually striking arms, the Perseus Arm and the Sagittarius Arm. This tranquil, somewhat secluded placement bestows upon our solar system a truly serene existence. We are situated far from the bustling, more turbulent and potentially chaotic activity that often characterizes the denser, more energetic regions closer to the galactic core, where gravitational interactions are more frequent and intense, and where stellar explosions might occur with greater regularity. Within the gentle confines of the Orion Arm, the vast populations of stars, the expansive clouds of interstellar gas, and the delicate lanes of cosmic dust are distributed in a remarkable, quiet balance, allowing for long, uninterrupted periods of stability. These conditions are profoundly conducive to the patient development and sustained evolution of complex life, providing a haven of cosmic calm for billions of years. We are positioned approximately 2/3 of the way out from the galactic center, a distance that offers a clear, relatively unobstructed view of both the inner and outer regions of the Milky Way from Earth's serene perspective. The Orion Arm itself is an immense, elongated structure, a flowing river of stars and nebulae patiently tracing its path as the entire galaxy slowly, majestically rotates. It is a quiet, enduring journey through the galactic landscape, a testament to the grand, unhurried movements that govern the larger, more intricate structures of the cosmos. Our presence within this specific arm ensures a gentle, stable environment, a calm harbor within the immense swirling currents of our home galaxy, allowing for billions of years of peaceful cosmic evolution. The subtle, pervasive gravitational forces of the galactic disk gently guide our solar system on its long, patient orbit, a silent, majestic dance within the grand celestial ballet of the Milky Way. This sense of belonging to a larger, yet equally serene structure underscores the deep interconnectedness of all cosmic entities, from the smallest asteroid to the largest galaxy, each playing its unique part in the vast, elegant, and unhurried unfolding of the universe. Despite this intricate and serene placement within the galaxy, the sheer scale of our local cosmic neighborhood can be profoundly humbling when compared to the galactic whole. The solar system is vast, spanning over 100,000 astronomical units, yet it is a tiny speck within the Milky Way. To truly appreciate this immense contrast, let us gently recall the measure of an astronomical unit, or AU, which serves as a fundamental cosmic yardstick. Our sun, a distance of c, imagine a vast ethereal sphere of influence, a silent, pervasive dominion extending outward from our sun for a staggering 100,000 of these units. This immense expanse encompasses not just the familiar orbits of all the major planets and dwarf planets, but also the distant icy realm of the Oort cloud, which we explored earlier as the source of long-period comets. This colossal sphere, representing the outermost boundaries of the Sun's primary gravitational dominion, is truly immense by any human standard of measurement. It is a vast expanse of space where our star's gentle, yet enduring, gravitational pull still holds sway over countless icy bodies, patiently guiding their millennia-long orbits. Within this immense, tranquil volume, the Sun's light becomes increasingly dim, a distant, gentle beacon against the profound darkness, a quiet, pervasive presence that slowly fades into the cosmic background. Yet, when we gently zoom out, when our perspective quietly shifts to embrace the truly colossal scale of the entire Milky Way galaxy, this immense solar system, which felt so boundless just moments ago, shrinks into an almost imperceptible point. Our home galaxy itself spans an astonishing distance of approximately 100,000 light-years in diameter. A light-year, as we know, is the distance light travels in 1 year. And it is a measure so vast that it represents roughly 9.5 trillion kilometers, or almost 6 trillion miles. To grasp the enormity of this galactic scale, consider that 1 light-year is approximately 63,241 astronomical units. Therefore, our solar system, with its 100,000 AU span, represents only a tiny fraction of a single light-year, making it an infinitesimally small dot within the galaxy's grand, majestic design. Despite the incredible vastness and complexity of our local planetary system, we are but a minuscule, almost invisible component of the grand galactic tapestry. This humbling perspective encourages a deep sense of quiet wonder and reverence for the boundless scale of the cosmos, gently reminding us that even the most expansive local structures are mere whispers within the truly unimaginable dimensions of the universe. Our solar system, in its quiet, unhurried journey, is a delicate, luminous particle within the majestic, swirling ocean of the Milky Way, a testament to the elegant hierarchy of cosmic scales, where local immensity is constantly dwarfed by the ever greater expanse beyond. The gentle, silent presence of our tiny system within this galactic behemoth underscores the profound beauty and serenity of cosmic existence, a constant reminder of our small, yet cherished place in the grand scheme. Finally, as we contemplate the outermost limits of our solar system, it is important to understand that these cosmic frontiers are rarely abrupt or sharply defined lines, but rather zones of gentle transition. The boundary of the solar system is not sharply defined, but gradually fades into interstellar space through the Oort cloud. Imagine not a rigid, impermeable fence or a clear, definitive dividing wall, but rather a subtle, ethereal transition zone, an immense and diffuse region where the pervasive influence of our Sun slowly, imperceptibly wanes, and the gentle, pervasive presence of the interstellar medium begins to assert itself. This gradual fading occurs primarily within the vast, spherical realm of the Oort cloud, which we previously explored as the distant, icy reservoir of long-period comets. In this outermost region, the Sun's gravitational grip, while still present and strong enough to hold these icy bodies in orbit, becomes incredibly tenuous, allowing for a delicate interplay with the subtle gravitational fields of nearby stars and the pervasive magnetic currents of the wider galaxy. The icy bodies of the Oort cloud are still gravitationally bound to our Sun, but their orbits are so incredibly elongated and their distances so immense that they are also subtly influenced by external galactic forces. As one travels further and further outward through this vast, tranquil expanse, the density of these solar-bound objects gradually diminishes, becoming increasingly sparse, and the characteristics of interstellar space, its diffuse gas, its microscopic dust, and its faint magnetic fields, become more and more dominant. There is no precise, universally agreed upon point where the solar system abruptly ends and interstellar space definitively begins. Instead, it is a continuous, unhurried merging, a serene blend of two distinct cosmic environments. This gentle, indistinct boundary reflects the fluid, interconnected nature of the cosmos, where influences gently overlap and diminish over vast distances, rather than terminating abruptly. Processes that shape cosmic frontiers, painting a picture of a universe where transitions are rarely stark, but rather unfold with an elegant, unhurried grace. This quiet, gradual fading into the interstellar medium reinforces the idea that our solar system is not an isolated island, but an integral, seamlessly woven thread within the larger, boundless tapestry of the galaxy, a serene, enduring testament to the interconnectedness of all cosmic realms. The absence of a sharp edge offers a sense of fluidity and endless possibility, a soft, inviting threshold into the profound unknown, beyond the familiar comforts of our home system. A gentle whisper of the cosmic ocean that lies beyond. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the dazzling brilliance of newborn stars to the silent shadows of ancient galaxies, from the intricate web of dark matter to the faint whispers of cosmic background light. You have traveled through starry nurseries, soared along luminous spiral arms, and glimpsed the heart of the universe glowing softly across unimaginable distances. You are part of this cosmic story, not just an observer, but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the legacy of distant explosions. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, and cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.